on your camera to on your camera as well. Yeah. So do join us for this what do you call it session. Okay, very good morning to everyone. Welcome to the micro machine learning deep learning workshop. From the Social AI Studio. So this studio really is to I think all of you here are actually helpers and group students for two projects mainly. Later we'll talk about the projects and some of the project POCs are actually here with us as well. Okay. So come, let me get started on this. So right, the workshop really is to appreciate the annotation effort by the Europe students. So many thanks for all of your help. Over the past, I think close to half a year, I guess, right? I think about 4 months or so, on annotation efforts from both the hateful memes classification team and the politeness dialogue team. Okay, you guys have put a lot of effort to annotate the data that contribute to quite a fair bit of our research. Okay, and many of the things that you are doing also have wider social implications, not just research. So, for example, for hateful meme detection, it will be deployed in hopes that to improve the safety of our online community. And for the politeness one, likely A star might take it over to deploy it for some commercial users for dialogue system and chatbots. Okay, so many thanks to all your effort on this. And I think and I hope that the annotation and data collection segment of this journey with us, right, give you some ideas on the many of these machine learning and deep learning projects, right? One of the biggest you know so-called biggest effort, I would say, and the most tedious part is really to collect and annotate the data. So you guys have done through this, okay? And of course, we don't want to just have you guys here with us to just do annotation and data collection. So that's why we thought it'd be nice that we conduct a workshop on this and to introduce the small projects also, for us to help you build your portfolio. Okay, so we hope that through this workshop and this project is also interest in AI and machine learning. I think many of you are in your just finished your year one term three, right? So you finished data driven for minimally, and some of you might be considering to do a AI major or minor, right? So this might be the time to explore further on this. And some of you have already taken the machine learning and other more advanced courses. So do help out, your peers as well, your juniors, in the midst of this workshop. Okay. And of course, lastly, is really to build a portfolio. Later, I'll tell you all why. Because we actually, want you guys to do two projects. Basically, some coding projects at the end of this shop with us. The projects will be closely related to what you have done for annotation. So there'll be two teams. One team will be doing hateful meme classification. The other team will be doing politeness classification. So at the end, you'll be building some machine learning models to do the prediction and classification of these two tasks. And there will be a GitLab repository for you to showcase your work so that in future when you're applying for internship or even for jobs, you can take this as part of your portfolio, okay, to showcase to your future employers. So that's the schedule for today and Friday. So you'll be two morning session. Yeah, after this, I think Daniel will take over to talk about introduction to ML. And Ming will be covering on the bell of words and vision tree. So that will sum up for today. So today we'll be looking more on the machine learning part of the house. Friday, when you come back, Zichang and Rabu will introduce you guys on the what do you call it, the deep learning part. Okay, so this will be on Friday morning itself. Okay, I think most of you should be able to join us for that part. I realized that I've skipped the slides. It's a bit laggy. Okay. So I didn't introduce the organizing team. This micro workshop is really done by the four of them, right? Ming Shan, Chang, Daniel, and Prabhu. They will be, you might be familiar with some of them, because when you're working, because they are the lead, I think Ming Shan and Zichang, they are the lead POC for the hateful memes and the politeness project respectively. Daniel is my PhD student, so he'll be giving the introduction to ML part. Rabu is my students, master students from Canada. He's actually based in Canada, which is why all the workshops are in morning. Actually, it's at night on his side. So yeah, we are very appreciative to have him with us to cover some of the deep learning component as well. Okay, so that's for the organizing team. Right, so I want to tell you more about the Europe project itself. I don't want to take too much of the time. But the project, right, is supposed to help conclude your Euro engagement with us. Okay, so I think respectively, the POC, Mingshan and Zichang will tell you about when is the expected end date for the annotation, which I suspect is sometime in, I think, mid-January, so about 15 January. Okay, and after that, the Europe phase one for the annotation will conclude. Of course, we welcome you guys to continue to join us for the rest of the annotation. And of course, for the next phase of the annotation, at the end of it, there will be another workshop, there will be another project showcase, so on and so forth. Okay. But that's for the later part. I'll leave Ming Chan and Zichang to talk to you guys more about it. Now, the project is ready for you to use as a portfolio, as I mentioned, for internship and job application. It will be hosted and linked to our studio website. Okay, so you'll be permanently there. You can use it. You can always visit it later part. Okay. Um, right. So for the hateful memes classification, the task is basically doing prediction. So given a texture so actually we try to convert and give you the text features of the memes this time around. So given the texture feature of a memes, your task is to classify whether the memes, build machine learning models, deep learning models to classify whether the memes is hateful or not. And for politeness, you'll be given a sentence, classify whether it's polite, impolite. Now, many of these memes, right, and the politeness classification, right, the data that we are using come from you guys. So it is based on your annotation that we are doing this. Okay. Yeah, and this is the link to put up your Europe projects. Okay. Let me open up. Okay, so as you can see, there's two projects here. Maybe I open the politeness one. Okay. I've give you some simple format. Basically, all of you, as per your annotation team, let's look at the team. What is a team to actually fill up this information? So for example, you can introduce the task, what is this task? And you can give some description, some examples of it. Then you can describe your data collection and annotation efforts. This one, Zichang can help you out with this. Uh, what do you call it? The project IC can help you out on this. Then exploratory data analysis. I think if you have done your data-driven work, you probably know what to do with this. Basically, to give some statistics on the data set that you have annotated, show some pie chart, show some bar chart, to introduce the data set itself. Then comes the politeness classification task. This is what will be covered in the micro workshop today and on Friday. So we'll be implementing some of these models for this task. Okay, and then you can put up the results and write your analysis on this. So treat this just like treat this just like like a block of a sort, for you to put up your codes, your data set, and a short write up on what was being done. And yeah, that actually sums up and concludes your Europe adventure with us. Okay, so that's for this. So after this, do send me your email, or if you have a GitLab account, you can send me the account and I'll drop you the invite to your respective folder. Okay, for this. Okay. So that's it for the introduction, the opening part. Should you have any questions? It's a very informal session, right? So should you have any questions with regards to the project, or some of the materials that's covered today, just feel free to drop us a text on Telegram. We'll be happy to answer you. Okay, I think that's all I have. I'll let Daniel to take over for the more exciting materials. Yeah. Okay, Daniel, you can share your slides. I think I have a lot multiple sharing.
Thanks, Roy. Can you guys see this?
Yep, cool.
Okay, so uh, today I'll be just covering this stuff. So first will be introduction to ML and its relationship to like AI and other I guess buzzword kind of things that you guys hear nowadays in ICT industry. Then I'll talk about features, dimensionality, and also like what's the general pipeline in a machine learning project. And then after that, there's some time for Q&A. We can take questions and things like that. Yep. So, right. So what exactly is machine learning? So basically, you can think of machine learning as a way in which we study computer algorithms which can automatically improve themselves. And they do this through experience, which in this case is the data that we feed to the algorithm to for it to learn. And based on that, the algorithm will um, basically try to learn a model or train a model using this training data and then make some kind of prediction or decision without us having to explicitly program the algorithm to do that. Now, you probably are wondering, okay, so ML is the study of how we can automatically improve, how algorithms can automatically improve themselves. So that sounds a bit like learning, right? Self-learning. So how is that related to AI, and how is deep learning, which is kind of popular nowadays, related to machine learning? Well, basically, artificial intelligence is a very, very big field that encompasses more than just uh, the math part of which machine learning is part of. Uh, it also includes like philosophy and also like other studies like in biology and things like that related to that. Uh, uh, and there are also like classical algorithms, which classical AI algorithms, which don't have any self-learning involved. So that is another distinct part from machine learning. And then we have deep learning, which is very popular nowadays, which is a subset of machine learning. And this is inspired by the work, a lot of the philosophical and kind of mathematical work done in artificial intelligence. And then thanks to technological advances, like with better computing resources these days, we can actually put into practice um, the theories and the math that was like discovered and formalized like in the 1970s. Yeah, so like I mentioned earlier, so what exactly is deep learning? It's a type of ML technique, or it's a set of ML techniques which is based on this concept of a artificial neural network, uh, which does representation learning. So neural networks, basically, they're trying to mimic the structure of the the structure and function of the biological neural network by allowing a form of distributed computation, which is what actually takes place in biological neural networks. So this distributed computation basically means like every artificial neuron is performing some kind of computation, and it is not necessarily the same computation, but it is computation, and then it all gets aggregated and then basically contributes to the final output of the model. Yeah. So talking about ML and like mathematical functions, one way, like one high level way that we can understand ML is simply as the learning of functions, because basically any model that we can think of can be represented in mathematical terms. And this model tries to describe the relationship between input variables and output variables. So for example, like you can see the equation below, there's a function of theta and x. So x is like the real world data that we encounter, the so-called experience that the algorithm has, or is going through in order to learn. And the theta are basically the parameters of the model, or in this case, I mean, you can think of it as the weights of the coefficients of this function. So that is essentially the mathematical analogy that we are that you can think of when you approach an ML problem in general. So, and like I mentioned, so this deep learning is basically like mimicking the distributed computational power of the biological neural network, right? So in the same way that ML is about functions, deep learning is also about functions, but it's a bit more high level now. So each neuron actually represents a different function with its own set of parameters. And the inputs of the neurons in the higher layers are fed into the lower layers, right? And so these connections, they are basically passing information to each other. And you can think of it as a form of function composition, because you can think of the neurons in the higher layers as one function, and then they're passing their outputs into the second layer, which is also another function or set of functions. So in this case, if we have like, for example, a three-layered a neural network, but heavily simplified such that there's only one neuron, you can see like the input passes to function C, and then the output of that is passed to function B, and then to function A, and then finally you actually get this output function X. But it's actually just composing the different functions together. So that's how you can think, a very high level way to think of deep learning. Right, so now that we kind of understand what exactly ML and its relationship to math, like how we implement it mathematically, and then subsequently how we program it in terms of like computer programming. How exactly do we go about learning, right? What is the mechanism by which the algorithm is able to determine its whether it is performing well or not? So basically, in order for the algorithm to learn an optimal model, right, it needs to find an optimal set of parameters, which basically means, if you think of it simply, you can think of it as the set of parameters which is able to allow the function to map the input data to the output labels or output variables with as little error as possible. Excuse me. So we can think of it as a form of optimization that's going on. And to accomplish this, we basically need an objective function, or commonly called a loss function, which is a mathematical way of guiding the learning process. So if you're familiar with, or maybe you may not be familiar with it, but there are some early machine learning algorithms which do not strictly use a loss function to guide the learning. So it's basically like they do trial and error, and then it's just either yes or no, whether it's right or wrong. And then that's how they tune the parameters. But nowadays, we have more sophisticated loss functions that allow us to basically target the algorithm to target different things so that it can learn in a better way. Right. And then what are the phases of basically this learning process? So we have, in general, in the learning itself, the evaluation of the learning, we have basically we have three phases. The first phase is the training phase. So we use the training data to basically get the model to learn an optimal set of parameters for that data. And then subsequently, we do some evaluation of whether those set of learned parameters are actually optimal. So how do we do that? We test it by taking a smaller subset of the training data that usually we set aside in advance, and then we feed it to the algorithm and get it to give us the outputs, and then we score those outputs and see, okay, does it, is the performance good or bad, that kind of thing. And then based on that, we can decide, okay, if it's no good, then maybe there's some things we need to change, right? So this is kind of like a feedback loop. So you can think of it as like in analogy to like a human learning, right? You do like a test in primary school, and then like the teacher gives you like a bad grade, and then your parents scold you. Okay, then so then now you know, okay, you need to buck up. You need to do something different, right? You need to learn, right? Or maybe like you did well, so then you know, okay, this thing works, so don't change it. So it's a similar concept, right? And in the testing phase, basically it's like, okay, now you graduated school, so now you have to go into the real world and basically use whatever things that you learned before that, uh, and try to like basically navigate through whatever is out there. So that's basically what the testing phase is. We typically that's when the model is exposed to like data in the wild that like we don't, not necessarily that we curate, but that it may be used like in a live setting, like in Google or Facebook, for their search algorithms or social network recommendation systems, things like that. Right. So now that we kind of get an understanding of what is machine learning, how it's related to AI, and how deep learning fits into this picture, uh, we should also understand that there are actually different kinds of learning that takes place as well, right? So I think you guys are familiar with like annotation that you've done, right? So annotating is like a form of labeling. You're basically taking some kind of input, and then you are giving it an appropriate label uh, for these various kinds of input, right? Um, so typically for labeled data, right, the kind of task that we use it for is a supervised learning task, which means that we are formally, what it means is that if you're given a set of data and a set of corresponding labels, you basically want to learn the function that maps the input to the corresponding label. And examples of these are basically classification and regression, which if you have gone through data-driven world, I think you should have two examples of it, of these types of models. Like for example, for classification, you have logistic regression for a two-class classification task, and then for regression is basically linear regression. And then you have other things like structured prediction, which is basically extensions of classification. So yeah, so basically like for every input, like data point, you basically want to map it to the corresponding label. So we call this associated label, right, for each data point as the ground truth label. And during the training time, the algorithm has access to both the input data and the ground truth label. So this is necessary because it's trying to learn the mapping, obviously. So then in that process, we try to have this model to give us the output which matches the ground truth. In the case of classification, like we want it to be strictly the same class as the output of the model to be strictly the same class as the ground truth label. So for example, if you're trying to classify whether there is a cat or a dog in the image, right? We want it to strictly tell us whether or not it is a cat or it is a dog, right? There's no in between for the classification. For regression, right? So it's you have a continuous variable rather than like I guess you can think of it as discrete, not discrete. Yeah. So instead of having like discrete classes, you have like ranges of values. So in that case, for regression, we want to have the output of the model be as close to the ground truth value, right? So it's slightly different, but in general, that's how supervised learning works. We try to get the model to learn the patterns in the data, right, by mapping the input data to its associated ground truth label or value, and that is the process by which uh, the algorithm knows whether it did something right or not, whether it is by evaluating how close it was able to get to the correct answer, the ground truth. So then, of course, there are various loss functions that need to be used for that. I won't go into it too much, but basically that is how supervised learning works. And the classification tasks that you guys will be doing basically are forms of supervised learning. Right, so then we also have another form of learning. I mean, we had supervised, so obviously that now we have unsupervised. So what does that actually mean? Basically, what it means is now that we don't have a label for the data. So in this case, rather than mapping, and also we because we don't have the data, right? So now it's a bit more tricky in terms of evaluating whether or not something has learned, whether the algorithm has trained a model that is able to perform the task well, right? So given the set of data, we learn the function that we map to some output transformation Z. You can think of Z as something like a label or value or a set of values, but we don't have a ground truth for this. So it's a bit different. And that's why for unsupervised learning, typically we use it for different kinds of tasks. So example is clustering, anomaly detection, dimensionality reduction. So what happens during unsupervised learning is that rather than the algorithm trying to give a form of signal to um like to the model, right, to update its parameters, like if I use like the primary school analogy, rather than waiting for your parents to um you know tell you whether or not something is good or bad, you basically try and do some self-reflection. So that is kind of what unsupervised learning is about. And so based on the patterns that they are able to self-learn from the data, then they can create the output. So for example, like in clustering, right? Let's say you have a bunch of um, a bunch of data points, right? And then you want to decide, and then you want to you beforehand you don't know whether or not like these data points, how the data points are related to each other. So maybe you want to find whether or not there are some like similarities between the different data points. So you can do clustering to kind of uh, identify whether or not there are certain groupings of these data points. And then that reveals something about the data also. So that is one way. And then also like, um, yeah, dimensionality reduction, I think I'll talk about it a bit later, so I won't cover it for now. Yeah, and then anomaly detection is basically like, uh, what is anomaly? Anomaly is like it's basically something that happens which is out of the ordinary. So in this case, right, why unsupervised learning is able to do things like this is because we get it to basically like learn the patterns for normal behavior. And then when some behavior that exists that doesn't conform to these patterns, we can basically identify that, okay, this is an anomaly or this is not something that we expected. Yeah. And why this is helpful is because like in the real world, right? Like let's say you want to train a computer system, a like a security system to detect uh, new threats, right? To the new like software vulnerabilities or things like that. It is infeasible to basically exhaustively provide all the possible kinds of intrusions or attacks on the software beforehand because you won't know what kinds of things exist out there, and because they constantly evolve, right? So we can't know as well. So what we can do is that we can gather samples of regular like computer software behavior, right? So then we can give a model uh, this data and get it to learn the patterns of that exist within a the regular functioning of the software. And then when something uh, out of the ordinary happens, right, then okay, the model is able to say, right, this is not okay. And so this is one example of why we also use unsupervised learning, because sometimes having a supervised approach doesn't make sense because of real world limitations. Right, so moving on, we've seen unsupervised and supervised. So there's also like a sort of in between, which we call semi-supervised, which what it means basically is that the data that you are given uh, is not fully labeled, meaning that there's a portion that is labeled and that there's a portion that is unlabeled. And typically what's involved is that we try to get the model to learn a function to map the unlabeled data to some label that we know exists based on the labels that do exist. And examples are transductive and inductive learning, which are basically like uh, trying to mimic uh, like the human induction process and things like that. Like, so like I mentioned, basically what the model tries to do is it tries to learn the relationship between the portion of the data with the labels and with the ground truth. And then and then from there it does like some, you can think of it as a form of like extrapolation or interpolation of sorts, right? Basically looking at uh the relationship that it learned from the labeled data and then try to apply it to the unlabeled data to give us plausible labels for those data. So if you go back to the primary school example, you can think of it as, okay, you learn some, like you learn as a child, you learn ways to do things in primary school. And then now you graduated primary school, you go to secondary school. So based on what you learn in primary school, you obviously try to use it to navigate your way through secondary school, right? So sometimes it works, sometimes it doesn't. But basically that process by which you try to apply that experience to some some new phenomenon or whatever is similar to what semi-supervised learning is trying to do. It's trying to take, and oftentimes a limited portion of a limited amount of labeled data with its ground truth, learn something from that, and then uh, basically try to use it for new data that we're interested to have labels for, right? And of course, how well the algorithm is able to do that also varies. So uh, right now there are like a few different semi-supervised uh, approaches to like data labeling and data augmentation. So like for example, what we might do is like if we have access to an even larger corpus of data, like careful memes or like polite or impolite conversation, right? The we can use the annotations that you guys provided to train a model that then we use to label as well. Those are the data. Yeah. And then the last form of learning that we have is uh, basically completely different from the previous three types. So this type of learning is called reinforcement learning. And basically, uh, I think data-driven world has something similar, like you guys have to move like some robot in a simulated environment, if I'm not wrong. So how does the robot, like, okay, in lieu of programming, like um in lieu of programming like certain hard-coded functions on how it should navigate around like obstacles and things like that, right? One other way to do that is to use reinforcement learning. So we define we define a set of states for an agent, in this case a robot, and then the environment, which is like the simulated environment in which it's going, trying to traverse. So, and then we also have a set of actions that agent can take, which is basically like, okay, if it encounters an obstacle, does it stop? Does it turn left, turn right, that kind of thing? And then we also have this thing called a reward function, which is basically similar in a sense to an objective function, but it's a kind of indirect way of doing it. And then after we have all these three things, we try to learn a policy. So what a policy is basically like saying that if a function that basically takes in a state and an action and then tries to calculate whether or not taking a particular action and transiting from one state to another will give you more rewards or less rewards. And then the reward function is basically how it tries to compute that. So the goal of it basically is to get the agent to maximize the expected cumulative reward. So some simple like things that you can do to explore reinforcement learning, because I don't think we'll be covering it much here, It's like, for example, you can, I think Facebook or Google like has some toolbox for AI that includes like things like moon lander or like car racing. So you can try to like implement a model that basically tries to play the game and learn the experience, and then based on that, like improve itself. So in the same way, like as humans, right? Basically, you can think of it as like, okay, so you know that if you know that you will get scolded every time you perform poorly for a test, uh, you will basically learn, uh, you will learn not to do that. But before you could do that, nobody tells you whether or not you get scolded, right? So you basically have to explore whether or not studying for a test or not studying for a test will get you scolded. I mean, sometimes maybe you don't study for a test, but the test is easy and then you do well, so you don't get scolded. So then you learn a policy like, okay, if the test is easy, I don't really have to study for it. But then maybe you encounter a test that's hard. So that's a different state, right? An easy test and a hard test are different states. So then you try, okay, I don't study so much for this test. And then you realize you got ranked super hard. And then your parents like gave you a new SO or something like that. So yeah, then you learn, okay, this is like the reward function in your head basically is like, okay, this is a bad idea. So then you learn, okay, for a hard test, don't uh do less studying, do more studying, that kind of thing. And then basically that's how you navigate uh through the environment, or in this case, like if you're a student, through your university life or whatever. Yeah. And so like this is a diagram that basically gives you a rough idea of like the different kinds of application and subtasks within these kinds of various learning. So semi-supervised is not included here because there's kind of like an overlap between the two. And depending on like how you design it, certain algorithms, you can actually like use them uh, for similar tasks in like supervised learning or in unsupervised learning. Yeah. So I think next is features. Yeah. So right. So we talked about what are the types of learning, right? So and then of course we saw also like the functions need some kind of inputs, right? So what exactly are those inputs to the functions? In simple terms, they are features. So what are features? Features, you can think of it as like a form of descriptive attribute for the data. So like for example, if you talk about an object in Euclidean space, we have features like mass, volume, velocity, things like that, right? So features can be found in the raw data. So uh, for example, like the mass of uh, an object, we could consider it to be a form of like feature in the raw sense, because we don't have to do much derivation to arrive at this quantity like the mass. But we can also derive or compute uh, features as well. So what typically this means is that we combine uh, other like more basic features to get higher level features, uh, such as in the case of like the object description, we have things like momentum, which is a combination of, I mean, it's a product of mass and volume, but in or density, which is uh, oh, right. Okay. Anyway, the size of the lettering is off, so sorry for that. But basically, right, what we can think of it as is there are simple features, basic level, and then there are higher level features. So the higher level, typically the higher level it is, right? Uh, the more abstract, I should say, not abstract in a sense, but uh, typically the features that are derived from lower level features sometimes can be more descriptive, and sometimes it might be closer to like abstracting away details, right? So, but that depends on the application that we are or the type of domain that we are looking at, right? So for example, in image classification, right, we have something called a convolutional neural network, which basically has filters which tries to capture patterns in the pixels of the image. So at the low level, the features are basically like very basic details. Like you can't really, like for example, detecting faces, you can't detect any facial features whatsoever in the lower levels. But when you go to like the higher level features, you start to see like actual like human like features, like for example, nose or eyes or like um ears, things like that. But at the low level, you can't really see it. So these are examples of derived features and so-called basic features. Right. So then how does the ML algorithm use these features to learn? So um, basically, right, as we try to make the distinction between different classes or different data values or sets of data values, right, as much as wide, I mean, we can distinguish it as easily as possible, as distinctly as possible. We typically try to use more features to describe each data point. So in theory, that leads us to better, uh, to having a model with better descriptive power in theory, because there's always cases like that you have too many features and some features are basically performing the same function as other features. So then you don't really need them. But we can't really know this until we actually try to train the model, right? So I'll talk about, I think, evaluating it later. And this is, and that's also why we need evaluation, basically. Right. So then we talked about features, and then now we need to talk about dimensionality because they are closely related to each other. And what exactly is dimensionality? So dimensionality refers to basically the degrees of freedom that the data can have within a space. So in a Euclidean space, you have data points with 3 dimensions because they correspond to each degree of freedom in that space. For example, the x-axis, y-axis, and z-axis, right, in Euclidean space. So how we represent this, for example, so how you can represent like an object, for example, to a ML algorithm is to basically like represent it as a set of vertices, right? And then each vertex has like a coordinate. So then what we do is basically we have these 3 dimensions, right? And then we basically have a set of this. So we have a vector of basically three or I should say we have a matrix with n number of points, which is the number of vertices for the object, and then uh is n by 3, 3 being the dimensions uh for the Euclidean space. And so what's the deal, right, with all these dimensions? So basically, right, um and what's the deal with like features? So basically, excuse me, so sorry. Um, so basically you can think of it as like in Euclidean space, there are basically like 3 features describing a single point, which is the x position, y position, z position, right? And then let's say you want to increase the descriptive power of this of some algorithm that is trying to learn like different 3D objects or something. So you have the set of vertices, right, with their coordinates. Then maybe to improve it, you want to add more features, like what are like the 10 nearest neighbors for each point, or 5 nearest neighbors for each point, that kind of thing. Or like if something, if you have a line being formed or something like that, then you have a list of vertices which are in that line, things like that, that kind of thing. So, or even the number of straight lines or whatever. So when you do this, right, you increase the number of dimensions which in the vectors which are being given to the algorithm to learn. So what that does is actually that every dimension you introduce actually increases the volume of the space in which the data resides. So in just the basic sense, right, in Euclidean space, you have the 3 dimensions. The data resides strictly in 3 dimensions. But the moment you try to incorporate more features, right, you increase the number of dimensions. So for example, if you, for each data point, you included the 5 nearest neighbors, right? That's another dimension that you introduced, right? And then now the object in its description does not strictly lie in a 3-dimensional space anymore. It's moved to a 4-dimensional space, or n-dimensional space, depending on like how many features you append to describe it. So what happens is that your space, the dimensionality has increased, but the number of data points you has stayed the same, right? So basically now your data is sparse because some dimensions are more empty than others, or in some cases they're equally empty. And what happens is that if you look at this data in a high dimensional space, they appear very dissimilar from each other because the space is so empty, right? If you try to cluster them together, basically you will get like clusters of just 1 or 2 because, you know, the space is just too large, and every distance then between objects then becomes large, but relatively speaking. So what happens is that in order to overcome this problem, right, if you have a more descriptive model, you then need more data for it to learn, right, the proper parameters in order to describe something. And then in the past, this used to be a problem because data, the rate at which we gather data last time is very, very slow. But nowadays, you hear things like big data, things like that, like social media companies, or like search engines, like harvesting data from users and things like that. And that's how they can train such powerful algorithms, because now they have access to greater volumes of data, right? So, but then, for example, like for hateful memes, right? We might want to train a system that, or a model that is able to detect whether a meme is hateful or not. But the problem is we may not have examples of, we may not have labeled examples of, a lot of labeled examples of hateful memes, right? So then there's also a problem, right? Because then the algorithm sometimes becomes intractable when you have extremely, I mean, at, uh, okay, so you might have something that works for maybe like a small volume of data, but the moment the volume of data increases, like your algorithm may become intractable, simply because it is no longer able to just, I mean, the assumptions by which you built the model no longer hold. So then how do we solve like certain issues with that? Like how do we solve issues with sparse data, with high dimensionality, and that kind of stuff? So one way that we can do this is dimensionality reduction, which is a subset of unsupervised learning, which I mentioned earlier. So how you do, basically how it solves the problem is you, in a very crude way, you reduce the dimensionality of the data. So what does that mean? It means essentially you take data from a high dimensional space and you try to put it into a lower dimensional space. Like you try to find a lower dimensional equivalent for this higher dimensional representation. And some ways you can do this is through feature selection or feature engineering in a manual pre-processing. But there are other ways, such like mathematical ways, such as principal component analysis, PCA, which you can think of as a form of factorization. So we try to factorize the high dimensional space, and then we take some of those factors that have the most descriptive power for that specific space, and then we use it as basically uh, we use those, right, the number of so-called dimensions we want in that are factorized, and we use those in lieu of the complete high dimensional space. And other ways is also like feature extraction. So for example, like I mentioned, convolutional neural networks, right? So the filters are extracting features from the images, right? So, but let's say you have an image, input image, right, that has a dimension of, like has a pixel dimensions of uh, like 100, for example. So then your input is actually a three-dimensional array, right? Because you have the RGB values, and then you have like the 100 rows, 100 columns. So that's a lot of data, right? I mean, there's a lot of dimensions, right? So then the convolutional neural network basically tries to extract the features out of those high dimensions and put it into a lower dimensional representation, which is what happens when you have multiple convolutional layers. And then finally the output of that, right, is actually like a much smaller vector, like maybe 100 vector with like 100 dimensions versus like uh, an array with like 100 by 100 by 3 dimensions. So that is like one of the ways in which we transform high dimensional raw data into uh, relatively low dimensional feature vectors. And this is something which deep learning does extremely well, and which is why it is very, very popular in modern machine learning and AI. Right. So then how does this all fit together? I mean, I've been giving you slight teasers by talking about feature extractors, learning phases, and things like that. But how does it all come together? So in general, right, you can think of a approach to a machine learning task as the following. You have a data pre-processing or data augmentation step, which is the very first step. And then after that, you have feature extraction, feature selection, feature engineering. These are all kind of similar. So usually they happen at this stage. And then, of course, you have the three phases of learning. You have the model training, and then you have the model evaluation, or in some cases, even feature level evaluation. And then finally, you train your model. You can test it with real world data, things like that. Right. So why do we need data pre-processing? Basically, not all the data you receive is very nicely formatted. Sometimes, like for example, if you're like pulling tweets from Twitter or something, sometimes not all the tweets have like certain information. Like for example, the tweet ID may be missing, or like the user ID might be missing, things like that. So then, to ensure that your algorithm is able to work, you need a form of standardized input. So then how do we do that? Basically, we need to pre-process the tweets, right? So we need to basically ensure that they all have the tweet ID, all have like the language, the tweet language, things like that. So then, either we remove those tweets which don't have this thing, or we have to manually edit them ourselves. Right. So I gave an example for retweeting, I mean for tweets and things like that. But for like images, maybe it's like resizing the image. Uh, or for the for example, a regression model, we basically ensure that each of the input features are the same for every data point. Yeah, so stuff like that, which we usually consider very trivial, but data pre-processing is actually one of the most important steps, because you can't learn a good model if you don't prepare your data well, because then, it's like the human body. You feed yourself junk food every day, you become a junk person. Same thing, you feed the model junk data, it becomes a junk model. So that's why we need to do all this pre-processing. And then, of course, we have data augmentation, which is slightly different, but it's usually done at the same stage as the data pre-processing. So sometimes existing data on its own is insufficient. So how can we increase the performance of the model? We basically have to augment the existing data, either by doing certain like transformations, such as image rotation, or we have to do other things like downsampling and upsampling to fix things like class imbalances and stuff like that in the training data. So you can think of it as basically like if you are lacking certain things in your diet, you have to take supplements, something like that. You can think of it that way. It's a similar concept. Right, and then we talked about feature selection engineering and feature extraction very briefly earlier on, right? So basically, what exactly is feature extraction? So feature extraction is typically something that we encounter only in deep learning. Basically, what happens is that a portion of the deep learning model is responsible for extracting features from the raw data without any manual guidance or input, in a sense from uh, the computer scientists. And this is possible because, like we mentioned about the distributed computational power of the artificial neural network, right? Each neuron learns a different function. So because we have multiple layers and we can specialize each neuron for learning different parts of the raw data, essentially that allows us to distill down the information and then gives us a very distilled representation for maybe different objects, like for different images or different sentences, things like that. And that thing that we get out of that is the feature vector. So the process of feature extraction, basically you can think of it as like a food processor or something like that. Okay, maybe that's not such a good. Well, basically like it's similar to like the dimensionality reduction in a sense. You basically have a lot of like data point, a lot of you have a lot of information in the raw data that you have, but you don't need all of it. So you just basically find the data that is most relevant, the information that is most relevant in the data for the model, or in this case, the model finds it for itself. And then the flip side is that we have things like feature selection and feature engineering. So sometimes, like I mentioned earlier, like the raw data has certain explicit features or basic features. So you may not want to use all of them. So sometimes you would want to select a subset of those features to be used. Like for example, a regression model, sometimes maybe you don't need all the 100 features. Maybe you only need like 25 of them to actually train a, a model which works sufficiently well. So then you can do things like feature selection, right? You choose the ones which have the you do some testing, find some correlations, and basically you choose the features which seem to have like certain higher correlations or things like that, and then use it to train your regression model, right? So then on the flip side is the case where you have less features than what you need. So in this case, you have to derive or compute or engineer basically new features from existing features. And like we mentioned before, it's desirable because more features increases the descriptive power of the model, right? But of course, you have to, like we mentioned, we have to keep it in balance also, because sometimes too many features is not good because some features are redundant. But what we want is basically as many non-redundant features as possible to increase the descriptive power of our model. And feature engineering helps us achieve that, because sometimes the features that we have, that the explicit features that are the raw data, is just insufficient. So we just have to do some engineering, for lack of a better word. Yeah. Right. And then, so in between this, we train the model and do things like that. And then finally we evaluate, right? So sometimes we just evaluate the model on its own, but other times, if we're able to, actually we would try to evaluate the features themselves as well, because allowing us this understanding, right, of what the model is actually learning, helps us to basically, it helps us in two ways. So in one, in an unsupervised approach, right, we are not explicitly telling the model anything. So actually the model is learning patterns, right? So these patterns are basically the features, right? So by understanding the features, we can basically understand the data, because then we can see the patterns in the data, right? So that's one way. And then the other way is, like, for example, if for a supervised learning problem, you have the features trying to, you have the features or the data trying to be mapped to an output label, right? So sometimes we want to, sometimes, like for example, for deep learning, right? For image classification, we don't explicitly design what filters or what the convolutional layers are trying to extract from the image. That's done on its own by the model. But what we would like to do sometimes is to understand, like, what features the model extracts, right? So then we have to do some kind of evaluation. But and this helps us, because basically it allows us to troubleshoot why maybe some models don't work as well as other models. And also, with this knowledge, we can basically design improvements to current models and improve the performance of existing models on, like, the various tasks. So if I were to give an example, for example, in a supervised learning task, you might have some raw high dimensional data, right? So then you bring it through the pre-processing, or like maybe for image, right? The convolutional layers act as a feature extraction layer, or feature extraction module, right? Then you end up with some low dimensional feature vector. And then you give it to some other fully connected layers, which are basically a classifier or a regressor, right? Then you get the model output. So for, even for like simple linear regression, right, it's still the same thing. So you might have a high dimensional raw data, then you do some pre-processing, select the features that you think are relevant, and then you end up actually with a lower dimensional feature vector, which is then your input to the linear regression model. So this kind of setup is pretty much the same if whether you are using like a deep learning on, or you're using just a normal machine, like a non-deep learning kind of model. But basically you can think of it as two stages. One is the preparatory stage for to process, extract features and things like that. And the second is the actual model itself. Like, this is the one, the regressor or the classifier or whatever model that comes after, that maps the low dimensional feature vector to the model output, is the one that is doing the so-called the actual mapping work, right? So that's where the magic takes place. And for unsupervised learning, so I mentioned before the idea of of anomaly detection, right? So one way in which anomaly detection is done is, like, for example, using something like an autoencoder, which, as the name suggests, it tries to automatically encode certain patterns or whatever into a lower dimensional representation, right? So how this happens is that you have high dimensional raw data, you feed it into some form of encoder module, and then you have a low dimensional latent representation or feature vector, things like that. And then you feed that into the decoder, which is like it's like the um analogous to the encoder, but it does like the reverse process. So then it tries to reconstruct the data. And then how we basically understand whether or not something is well learned, right, is basically when we see that the reconstructed data and the high dimensional raw data are very close to each other, right? So that's one way. And um, this idea of encoder and decoder is quite common for things that like where you are trying to learn latent representation or latent features about a data that you have, that you don't know anything about. And this basically gives you like a starting point. So for example, this setup, right, the autoencoder setup can actually be used as a way to do dimensionality reduction, right? So if the data that you're looking for, you're looking at, for example, does you don't really know much about it, or you can't really see uh explicit features or things like that, right? So what you can do is basically try to get a lower dimensional encoding from that. And then after that, you can take this latent vector, right? After this thing is successfully trained, you can take this and then you can use it as an input to something else, like a classifier or a regressor. So I know we presented the supervised, unsupervised, and all these kind of things as like distinct types of learning, right? But it's not strictly speaking, I mean, it's not necessarily that each of these happens like in silo only for a particular task. Sometimes you might utilize multiple types of learning in a single task, right? So I mentioned like in the context of software security or things like that, right? Sometimes the raw input data from the computer logging system is too difficult for us to understand, right? So then we do some form of feature extraction or dimensionality reduction, uh, in this case with the unsupervised model, right? We're basically trying to find the patterns for regular software use. We have this thing, right? So then with this, we can use it as an input to a single, like a one class classifier, which basically we try to just get this to learn the feature vectors of this, right? And then when it comes to detecting anomalies, right, then we can use that classifier. Okay, um, like if it encounters something that is encoded that doesn't conform to the patterns that it already has learned, right, then it will raise the alarm, things like that. So you can see that like the unsupervised learning and the supervised learning are both utilized like in the same task, but that depends also on like the task that you're doing. Not every task requires you to use both, or not every task requires you to only use one of something. But having an idea of like the different kinds of learning helps us to understand at the different stages of our design process what exactly we need, right? So that is basically the challenge that uh, the main challenge for us as machine learning scientists or things like that. Yeah, and I think that is it. So I'm not sure, do we have time for questions?
Yeah, I think we can take some questions. Anyone has any questions?
Yeah, sorry for the information download. I know it's quite heavy, especially in the morning, but like these are basically the kind of conceptual building blocks that you need to understand the high level stuff I mean, it gives you a very high level understanding, but it is helpful because then when you try to understand the low level workings of things, right? You have a conceptual model to go back to relate back to.
Hello. Bit confused about the unsupervised learning is why do you want to reconstruct with your raw data you encode, then you decode your to reconstruct back your to get the raw data reconstructed back. Is it
And
just like a bit denoising or
you're talking about in this case, right?
yes.
Okay, so so this is a very specific example of unsupervised learning, right? Like, there are others like clustering or that don't follow this pipeline. But in this case, right, of like autoencoder, why you want to reconstruct the data is you want to I mean if we think of it as functions, right? This is one function, this encoder is one function, and this decoder is one function, correct?
Mm-hmm.
So in the ideal case, the encoder and the decoder, they are related simply by this being the function f and this being the function f inverse. Make sense?
Yes.
Yes. So then if we learn a good encoder or we learn a good function, right, to help us to distill the data to this lower dimensional state, right? This lower dimensional latent vector or feature vector. Conversely, the the inverse function should also have been learned, also has to be learned well, right? And how we can know that this whole process is going well is that if we have this thing going in and coming out, right, and we get back as close to the original input as we get, right, then we can conclude that usually with high amount of certainty that these two functions are basically correctly learned. And because we have no explicit supervision, like for example, in the case of like learning a lower dimensional vector, right? Doing some kind of dimensionality reduction, we don't have a form of supervision to tell us whether this thing is correctly mapped to this thing, right? So what can we do in lieu of that? The mathematical trick is basically, f inverse into f, right? Sorry, f inverse of x into f basically gives you back x, right?
So
But
it's like a way to check back, right?
yes, exactly. So you can think of it as checking back. Yeah, exactly.
But actually, what does the low dimension latent vector is just you having just showing you the feature more prominently, right?
Okay, so it could also be, right, that so for I mentioned that sometimes we use autoencoders to learn for like anomaly detection or things like that, right? And sometimes the input data is very, very high dimensional and it's very, very abstract from a human sense. It doesn't make sense when a human views it just as it is. So sometimes we want a representation that we can kind of relate to more easily, right? So that is what a lower dimensional latent vector or feature vector is for us, basically.
It's like making it more visible, right?
Yes,
Less
visible,
confusing, right? Cleaner.
yes, less confusing, more visible in a certain sense. Also, sometimes it may reveal hidden patterns in the data. Like, for example, like there might be a lot of numbers here, right, that you can't see like how they're related to, right? But after you distill it down, maybe you can find it encapsulated in one particular dimension of this latent vector, right? Maybe two or three dimensions here correlate to one dimension here. You can't see it here because there's just too much data for you to I mean, there's too many dimensions for you to basically draw patterns across. But from a lower level, right, after you distill it down, I mean, this thing basically does the distilling for you. So now you know actually what are the things, that influence like the various like variables here, right? in that sense. So that is one reason why we need dimensionality reduction. And the other is also sometimes we can't see patterns, right, necessarily when the dimensionality of data is high. Most human beings don't have that ability. So, but in low dimensions, right, when the patterns have already been learned and they have basically been you have some kind of like corresponding variables here that basically describe a particular pattern, right? You can use that in lieu of looking at this high dimensional data, right? So this thing reveals patterns and 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 things that we cannot see from here with the naked eye. In the same way, right, that if you were to sometimes if you were to just give a raw high dimensional data to a classifier, right, uh, the classifier itself may not necessarily be able to learn everything extremely well because there's a I didn't really talk about this. I think it's a bit more complex, but uh, basically like for in the context of deep learning, your classifier is usually a bunch of fully connected layers, right? But the learning power of that classifier is dependent on how many hidden neurons you have, because like we mentioned, each of them is a function, right? Sometimes the data is too high dimensional that these individual functions within that classifier, there's not enough of them for you to basically learn something very well. That's why we need these other tricks to basically distill the data for us. Or if not, what we have to do, right, is we have to create like a very, very big multi-layer perceptron, like a lot of fully connected layers, like maybe 10 layers or something like that. But you know what's the problem with 10 layers? The problem with 10 layers is you get a lot more parameters as well. That's one problem. The second problem is, how do you know what's happening within those individual layers? Like maybe there's a lot of spurious correlation involved. Maybe like some of the neurons itself, the functions are not learning properly. They're going to zero, right? You don't know. And it's very hard to know because the more layers you stack on top of each other just like that, right? And assume that you'll solve a problem, sometimes it doesn't really solve the problem at all. And in fact, it creates new problems. So why typically, right, when we have like classifiers, right, at the end of like some form of machine learning pipeline, we don't make it super deep. It's so that we can also understand the classifier. Then in lieu of the classifier learning all these relationship between high dimensional data, we basically have something else to do the heavy lifting for us, which is like the encoder or the feature extractor or things like that. And then we also then try to understand also what is being extracted and what's being encoded and things like that also. But it's easier because we kind of split them up. We don't take them all as one chunk. Sometimes it's easier to analyze a function, right, if we split it up into smaller functions, right? Because we can isolate behaviors and then we can do troubleshooting. You know what I mean? If we take it just as one huge function, like we mentioned, right? Like the deep learning, if we don't think of it as function composition, we just think of it as one huge function. How do you figure out which part of the function which, parameter, for example, or the set of parameters is messed up? It's very difficult, right? So we kind of make it simpler by reducing the size of the building blocks that we have. Then we can analyze each of them, in turn. And it's easier that way because then the things we have to look at are not so huge in a sense. Are not so complicated, right?
I see, I understand. So actually this way is, do you like, if there are a lot of layers, is that how you keep checking back? You encode, then you have run an inverse, then decode to check whether
Uh,
it can go back. Like you
okay,
don't
so
lose information.
right, so it is possible to do things like that. Another thing that I would highly recommend for you to be able to understand why the function composition understanding of deep learning is so effective, right? Is, for example, if you look at image classification model like ResNet. Are you familiar with ImageNet?
I see my friends do before.
Okay, yeah. So you can go and search like GitHub for like ResNet implementations, or even just search like ResNet architecture, like a diagram or something like that. And then you'll see, right? Actually, they are basically like blocks and blocks and blocks. But because each of them is a block, right? Rather than one whole just giant chunk of fully connected layers, right? They can analyze the behavior of each block, right? So, and in a sense, actually, not just in terms of image classification or things like that, even like you can think of like even like for textual tasks also, like there are also ways in which like we block kind of I don't know whether block is the right word, but basically, you know, we have ways of basically building specific modules to do specific functions, right? And then we have it as simple as possible so that we can analyze how the behavior of these modules work. Because you overcomplicate things, you do not know sometimes whether there's correlations between things going on that you cannot see, right? Like we mentioned, like that's also why we need this thing in the first place, right? Because most human brains cannot perceive connections in high dimensional space. But if you just take everything as one fully connected layer and then just plop it down there as one huge function, right? Like how can we debug that function if it doesn't work? We can't. So that's why we need to break it up, right? And in certain cases, yeah, you may need to go through multiple rounds of decoding and encoding. Actually, there is a kind of architecture called restricted Boltzmann machine, which is based on something like this. It's a probabilistic model, but it basically has the same kind of philosophy behind it. It's a basically encoder decoder kind of thing. You basically give it an input. It has a hidden layer. It maps it to some latent variables, and then after that, it tries to reconstruct the output. But what they do, so for example, one application of the restricted Boltzmann machine is that they built this thing called a deep belief net, or deep belief model, right? So what it does is actually you are basically stacking restricted Boltzmann machines on each other. And what happens is that then each subsequent layer, right, learns something else about the previous layers, right? So then that's the method of, you can think of it as like similar to convolutional layers, the high level features, low level features, and then you keep stacking them and it goes on, right? And eventually you get to distill the knowledge down to something that you can understand. So yeah, there are things like that where you stack like encoder decoders, encoder decoders, encoder decoders, but typically those are used in a particular kind of problem, right? So different problems require different approaches. So this is the approach for some kind of problems, but for other kinds of problems, it may not work so well, or you might have simpler solutions, right? So you know, you don't use a hammer for every single thing, right? Because hammer isn't the right tool all the time. Sometimes you need something else, like a screwdriver or something.
Yes, yeah, I understand. Thank you.
Sure, no problem. Do we have any other questions? If not, I think I need to hand over the time. Or is it a break
Yes.
now?
Maybe we can take a 3-minute break. Yeah, so that we don't take into too much time. Then just a 3-minute break to like refresh your mind, you know, go stand up, take a drink or something like that. Yeah. So I'll see you guys at 10:37. Yeah.
Okay, thanks, Mishan.
No problem. Thanks, Daniel.
Thanks.
Anyway,
If you
yeah.
yeah, if you guys have
Go
questions,
ahead.
right, we'll still be sticking around throughout. So like if you have questions even during the course of a presentation or something, but the speaker is speaking and you don't want to interrupt, things like that, you can, put it in the chat or something, and then one of us will try to answer it for you. Yeah.
Anyway, just to Jason, right? And also like anyone that's interested about auto encoder stuff, because I think we didn't want to make it yeah, we'll make the slides available later, right? Yeah. But anyway, we didn't want to make the auto encoder. The auto encoder was just like add on, right? Like something uh to spice things up, right? So we didn't really intend to go very detailed into it. However, if you're very interested in it, right, and you want to find out more, I recommend that you can start by looking at like principal component analysis, PCA, right? So that will give you a better idea and insight to why we perform dimensional reduction, right? And it will give you a better idea of like what's the purpose of the dimension reduction.
By the way, right, you guys, do you learn have you guys done like linear algebra yet? Because I think you would have covered a factorization technique called singular value decomposition, which is actually conceptually similar to principal component analysis. So if you know about that, like you can just read up further from there. Yeah, it has I mean, the core principles are still the same. So, I mean, pun unintended, but you can go from there, and then, yeah, because autoencoder is essentially like a deep learning way of doing PCA or factorization.
Okay, sorry. So I think we just wait like another 2 minutes more. Sorry. Yep. In the meantime, I will share my screen first, and I will also share the link to my presentation slides. Right. Yeah. I'll try to make it a bit more brief. Yeah, because I think guys a lot of information today. So I'll try to make it brief, and at the same time, I have planned to have like about 3 stops during the presentation. Like stops are like, right, for you guys to ask questions to clarify like if anything is not clear. Yeah. So let me share my screen first, then I'll start sharing the slides in the chat. Are you guys able to see my screen after I full screen it? Okay. Yeah. Okay. Thanks. Oh. Okay. So I'll probably start the session now. Okay. So before I begin, right, like I mentioned, for these PowerPoint slides, which I'll bring you through like the fundamentals of decision tree classifiers, right? I plan to have like about 3 stops, right, for you guys to clarify concepts and so that we can
check whether like am I going too fast or try explain more in depth. Okay. Then after this presentation or this like PowerPoint slide, right? Then we'll move on to a more hands-on session where we'll actually use a Jupyter notebook to actually do more on two things. Firstly, how to handle textual information or textual data, right? For example, reviews, posts, tweets, etc. Right? And then secondly is now that we process that textual data, we'll move on to training a decision tree on top of the processed data. Yeah. Okay. Okay. So without further ado, yeah, I will start the session. Okay. So yeah. So okay. So I will jump straight into the task first. So in this entire micro workshop that we are conducting, we will be focusing on the classification task, right? I believe most of you, or should be everyone, right, like have gone through the data-driven world, and I believe they should have covered this. Am I right? Like maybe some thumbs up would be good. Like if anybody can hear me, like classification task is covered, right? Okay. At the same time, then I'll in this slide I'll just briefly talk about the classification task. Then I'll also talk about how we do the training, validation, and testing, right? So first of all, the classification task, the idea is that we'll be given like a collection of records. Then each record will have a set of attributes, right? A set of features, attributes, depending on how you call it, right? Then one of those features or attributes will be the target class, which is the class you want to predict, right? So in the sense of hate speech detection, right, we can have many factors for hate speech, right? Okay, actually not really. Like, for hate speech, usually it's just textual features, right? But then if let's say you have if it's hateful memes, right? So from the memes, we can actually collect more categorical features or nominal features, category features, right? So like how many people is there in the image and etc. Right? That's the idea. Then obviously the target class will be whether is it hateful or not hateful. So the purpose of the classification task is that we want to find or train a model that can actually predict each of the record, right? To its like corresponding class as accurately as possible, right? So if I give it unseen record, unseen hateful record to the model should be able to predict that this unseen record is a hate speech or is hateful, right? That's the goal of the classification model. Okay, yeah. So that's how we do it. So we do it on a training set, right? So to the way we if I didn't make it clear, when we have the data set, we will split into a training, validation, and testing set. So three sets, right? Training, validation, test. So once you train the model on the training set, we have to ensure that the model is not biased, and then we can do a proper evaluation of the fit model, right? So to do that, we will actually test the learn model on the validation set first, right? So validation set is not part of the training. So when we test it on the validation set, it's actually like it's actually quite trustworthy, right? To say that if the model is actually performing well on the validation set, it should be it should not contain any like severe bias, right? Yeah. However, right, when you do later on we'll go through like in decision tree and stuff, there are some things that you have to tune, and these things are the model hyperparameters, right? The model hyperparameters can contain things like let me see, right? The easiest way would be like for logistic regression, if you guys have done it, hopefully, right? Then there's like this thing called we will go through later, right? There's this thing called L1 norm and L2 norm. Then these are things that you can actually tune as part of the model parameters, right? So the validation set might be also biased towards the selected hyperparameters, right? Therefore, once we have test the model against the validation set, we will test it again on another test set, right? So you can think of it as just like training, test, right? So the training here is to test, we'll perform the first test against the validation set to to obtain the best hyperparameter for the model, right? Then to ensure that the hyperparameter is not biased towards the validation set, we will test it on another test set, right? And that's the final test set. Yeah. Okay, actually, this is the first stop. Did I lost you guys here? Yeah. It's a bit hard to explain. Yeah. Any questions regarding here first? Okay. Okay, so I will continue on. Okay, so the first classification technique or the classification technique that we'll be talking about here will be the decision tree based methods. Okay, so in this case, like what it says, right? Decision tree is comes in the form of a tree structure, right? So technically, we can think of it as like building from the root, from the bottom up, or from from the bottom up, from the root up, right? So the idea here is, as we go down the tree, go down the tree, right? We'll break the data set into smaller and smaller subsets, right? While we develop the trees further, right? Like tree grows, then we will slowly develop trees. So firstly, we will start with a root node. Okay, sorry. So a decision tree, right, mainly contains, I would say contains three things, or two or three, depends on you, right? So the primary two things is a decision node. So a decision node is at every fork of the path, you have to make like a decision, right? Given a question, you make a decision. Is it a yes or no, right? Or you can even make a multiple ways, right? Multi path decisions, right? And then this will lead to a corresponding leaf node. Okay. Okay. So take a look at this image for a while, right? So first of all, we will start first that we are building a decision tree with the ultimate goal, right? Or the target class being that, should I accept a new job offer, right? So this is a classification task of yes or no, right? Yes, I should accept, or no, I should reject. So looking at the root node, the first decision that we will make, right? We will ask ourselves, we will probably like pick one of the features, or we, based on some measure or something. Then we'll ask the question, right? Is the salary at least 50,000, right? If the salary is at least 50,000, if the salary is less than 50,000, sorry, then we'll say no. I will reject the offer, right? If the salary is at least 50,000, then yes, okay. Let's see what's the okay. So just having a salary more than 50,000 does not satisfy me, right? I'm a greedy person now, okay. So I want more than 50,000 and I want more, okay. So now I ask myself, or I ask the employer, or I look at the job offer, I see, okay, does the commute take more than 1 hour, right? Because I really don't like to travel, right? Yes, it takes more than 1 hour, so I will decline the offer. If not, I'll move on to the next decision, right? So you can see like how this is flowing, right? That's why it's called a decision tree. And essentially, as like programmers, we can see it as like a if else tree, right? It's like if yes, do this, if not, do that, right? If else. Okay, so now let's take a look at an example, right? To better understand the way, right? So now that we are given like this transaction data or the training data, and we are tasked to train a decision tree, right? The goal here is that, whether someone will actually go and play Pokemon Go, right? That's the idea. So look at this, as a gamer myself, probably I will go with, I might start with something like this, like, does the person play Mobile Legend, right? If the person play Mobile Legend, then the chances is it's going to be a no, right? Because Mobile Legend is usually is quite like committed, right? So people commit like hours to Mobile Legend, and they prefer those kind of 5v5 battles more than the RPG kind of game. So as we can see, if we go by this route, people who play Mobile Legends do not play Pokemon Go, right? That's good. Okay. But let's take a look at people who don't play Mobile Legends, right? Then we will see that, people who don't play Mobile Legends has a mixed answer of do they play Pokemon Go or not, right? So now we'll take a look at, what is another feature that we can take a look to better separate people who play Pokemon Go and people who don't play Pokemon Go, right? So first we can take a look. So in this, we can see that there's actually three types of takers, which is single, married, and divorced, right? So here, we'll describe more in the about how it splits, right? It's you can technically split it like single, divorce, married, right? We'll talk about it later. But so now in this case, right, the way I see it is if I take a look at all the data set, I can see that people who don't play Mobile Legends, which is the yellow records, and people who are single and divorced, actually no, sorry, people who don't play Mobile Legends and who are married, right? They typically don't play Mobile Legends, right? See, no married, no, no married, no, and no married, no, right? So that's a good sign. So we know that this is good, right? People who don't play Mobile Legends and they are married, they just don't play mobile. They probably just don't play games, right? Yeah. Not absolute lah, just in this data set. Okay. Okay. So now we take a look at the other side of the house, right? Is this has this come to like a final decision, or is it like does it mean that everyone who don't play Mobile Legends, single and divorced, play Mobile Legends? Let's take a look. Then we will see that there's a mixture of answer again, of yes and no, right? So in this case, we can make another decision, which is that is the income less than 80K or more than 80K, right? So sorry, I see something coming up. Sorry. Okay. Okay, just give me a short moment. I think people wants the slide access. That's my forum. Give me a moment. Just a quick one. Okay, I think you should be able to access it. Let me know if you can access it. Okay. Yeah. Okay, continuing. Yeah. So yeah. So if you take a look at this, right? So now if you inspect again, we can make like okay, it's like if you were to plan the tree manually, we can see that people who have less than 80K actually don't play Mobile Legends, and people who earn more than 80K play Mobile Legends, right? So now we have finally come to the end, right? Where we sort out where we are able to sort everybody into their corresponding target class properly or accurately, right? So yeah. Okay. So yeah. So this part everybody is clear. Yeah. I just maybe 10 seconds. If anybody got questions, then can ask. Okay. If not, we'll move on, right? So just now, the way we selected it is like, I come from like maybe a gamer background. So I started with, do you play Mobile Legends? Then we go from left to right, essentially. But it's also possible, right, that you start off with like the marital status, right? Is the person married first or is it single and divorced? Then you go down another decision and another decision, right? So given a different tree, it can fit the data equally good, right, or equally accurate. Okay, so now let's take a look, right, based on the tree that we have developed earlier on. If let's say we apply it to a new record, right, this is the test data. Okay, let's try, right, from the root node we try to go down, right? So yeah, so first of all, we can see that if you play Mobile Legends, this person don't play Mobile Legends, so we go to the right. Okay, no. Then next, we take a look at the marital status, right? Then we will find out that, okay, this person is actually married, right? So our final prediction for this person who don't play Mobile Legends is married and earns 75K. The model will predict that this person actually don't play Pokemon Go. Yeah. So that's the idea, right? We train on past data that we have collected to predict on new data that we are seeing. So that's the idea. Okay. Okay. So before I move to the next slide, right? So you see, when we go through this example, we are able to look at the data and pick maybe like what is yes or no, or what is a good thing to actually branch out, right? However, right, actually we have to answer like 4 questions, right? First question would be like, how do we decide which feature should be the first feature, right? Which feature should be located at the root node, right? That's one of the questions. The second question would be like, what is the most accurate feature to serve as internal nodes or leaf nodes? Then third is how do we split or divide the tree, right? Like like I say, right, we like so far all the splits that we are doing is binary split, right? It's not a three-way split, right? For example, this marital status, we can do a three-way split. Yeah. Then lastly is, how do we measure the accuracy of splitting the tree? Yeah. So these are actually like the 4 questions that we would like to answer, or we need to actually answer, right, to develop the tree. Okay, yeah. So first of all, to grow the tree, we can take a greedy strategy, right? So the greedy strategy is that, we split the records based on the attribution test that optimize a certain criterion. Okay. So the criterion here would be that, we want to have a split where the leaf node is homogeneous, which is like all the classes, which is in this case, right, all the classes in the leaf node here, right? I don't have to go back another slide, right? But idea is all the leaf node, all the nodes, all the records in this leaf node are of the same class, right? That's what we want, right? Homogeneous, like pure classes, right? So that's the greedy strategy that we'll use. So then this is the issue now. So how can we actually determine how to actually split the record, right? How do we specify the attribute test condition? So first of all, to specify the test condition, it depends on 2 things. Firstly, what are the attribute types? And secondly, what's the number of ways we can split? Yeah. Sorry, give me a moment. Okay, sorry. Yeah, I'm back. So yeah, so it depends on 2 things: the attribute type and the number of ways to split. Okay. So for the attribute types, we have like nominal features, ordinal features, and continuous features. I believe most of you guys have actually gone through stats class, right? So this should be quite familiar. Yeah, then the number of ways to split, like I mentioned, we can do a 2-way split or multi-way split. Okay. Yeah, so first of all, looking at nominal values, we can do, like multi-way split, which is like what I say. For a car type, we can look at it family car, sports car, or luxury car. For binary split, we can look at we can actually technically divide the 3 values into 2 subsets, right? If you want to divide 3 values into 2 subsets, technically it's just 3 choose 2, right? Which is there's 3 ways, right? And regardless, if you do 3 choose 2, it means that one of the class must be independent, right? So in this case, we on the left, we put the family car as one path by itself, which is 1 split. Then we group the sports and luxury car into another split. Besides this, the other way, you could be sports, then family luxury. The last one will be like luxury, then family and sports. So this is how we can split for nominal values or nominal attributes. Then next, if we look at, ordinal attributes, right, we actually do the same, right? So for sizes, we have small, medium, large. Then similarly, we can divide the 3 values into 2 subsets. Small, medium, large, medium, small, right? So it's very, very similar to how we do with nominal attributes. Okay, so now that nominal and ordinal attributes are categorical features, right, or categorical variables. So they are similar in nature, right? But now how do we deal with continuous attributes, right? To deal with continuous attributes, we can use a method which is like this discretization, right? To perform discretization, right, the idea is that we actually form an ordinal categorical attribute, right? We'll look at an example in the next slide. But the idea here is we can, rather than, okay, so let's say for age, right? Age is like a continuous variable. Yeah. So age, if you look in terms of years, right, you can be like 25.1 years old. So the idea here is if you look at age, we can actually separate or we can bin, discretize it, right? Like bin it into like multiple range, right? So you can put into like toddler age 1 to 6, then you can put 7 to 12 as, then 13 to 18 as teenager, so on and so forth, right? We put them into bin and taking them as right. That's the idea. So so there's 2 ways to the way is manually, or we call it static discretization, which is that we discretize the continuous value before doing the classification task, right? So like what I said, right, 1 to 6 toddler, 7 to 12 children, that kind of stuff, right? Then for dynamic, right, it's more like as you build the decision tree classifier, right? The decision tree classifier will actually make like some kind of smart guess, or make will perform the discretization dynamically, right? So how can decision tree actually make this discretization dynamically, right? Is that they can use you can specify the model to use things like equal interval bucketing, which is binning in equal intervals, right? So for example, you have age of 1 to 50. So equal intervals could be like 10. So 1 to 10, 10 to 20, so on and so forth, right? Then equal frequency bucketing, which is like percentiles, right? So I think you all have learned, like, if through stats, you all should have learned, like, there's 4 quadra, right? Quadra, right? Yeah, quarter. Yeah, 4 quarter, sorry. Okay, so 4 quarter. So there'll be like 25 percentile, which is the first quarter, then 50 percentile second quarter, 75 and 100, right? That's the idea. Or we can do it through clustering, right? Then after that, we can do the same thing. We can do not wrong, three-way. Yeah, we can do a multi-way split or a binary split. Yeah. Okay. Yeah. So for binary split, one way we can see it is, we don't do any binning, right? If we don't do any binning, we look at the numerical value directly, and then we see whether can we find a good cut, right? To say that above a certain threshold, which in this case above 80K, will be a good split, right? But this is more computationally heavy because 80K is quite a random number, right? How do you determine the 80K, right? So you need further computation to actually perform this, right? So the other way you can do it is what I said. You do the discretization, then you do a multi-way split, right? So in this case, less than 10K go here, 10K to, I think this is upper bound, right? So like not, it was less than, right? Greater or equal to 10K and less than 25K. Yeah. Yeah. Okay. Then so on and so forth, right? As you can see. Okay. So that's the way we can actually define the attribute test condition. Then next, okay. Maybe I pause here for a while. Anybody have any questions regarding the attribute test condition? Or need me to repeat or explain something clearer? Okay, if we don't have, then I'll move on to how can we actually determine the best split, right? So to determine the best split, first of all, if before we split the data set or the records, right, we have 10 records of class 0 and 10 records of class 1, right? So these are the 20 records that we have. If we evaluate it based on 3 different feature variable, 3 different variable. So first, if you take a look at this, own car, then car type and student ID, right? Can you tell me like which condition is the best, right? Yeah. So yeah, if anyone wants to, yeah. Okay. Yes. Thank you, Chi. Right. So yes, you're right. The last one will be the best because if you okay, maybe we go from left to right, right? Okay, we go from right to left. Okay. So if you look at the last one here, you can see that this one, this student ID feature actually split 20 ways, right? 20 ways. Technically, it's 20 records, it's split 20 ways. Then it's very obvious that every single leaf node from this decision will be a single record by itself, right? And because it's a single record by itself, we consider the leaf node to be very pure, right? To be very homogeneous, right? Because the leaf node only contains one class, right? That's why it's very pure. Then if you look at the second one, right, which is the car type, if you look at this, we can see that the separation is not as good as student ID, obviously, right? But it's actually not too bad, right? If you look at these 3 classes, we can see that sports is by itself is the most homogeneous, right? Because if we classify by sports car, only people who own sports car belongs to class 0, right? And no one belongs to class 1. So this is like purest that it can be. Right? Then if you look at the family and the luxury category, it's actually not too bad, right? It's only one one flow over, right? Majority of them are in class 1, majority of them are in class 1. So this is also a rather good split, or rather good way to just a rather good split, right? Then for the left one here, as you can see, if you own a car, right? If you go by this variable selection or the decision if you base your decision off this variable, right? You'll realize that even if you do a split, actually it's not that good, right? It is still a 50-50 chance, right? 6-4 is like quite comparable to 5-5, right? Which is a random guess. So this is actually quite bad. So yeah, as we can take a look from here, we'll be able to see that what I mentioned just now is presented here in a more descriptive manner. So if we have a split, right, a leaf node, right, a leaf node with a 50-50, which is like half of it in class 0, half of it in class 1, then this leaf node is technically non-homogeneous, means it's not pure, right? It's impure, right? So which actually corresponds to the next line, right? Which is high degree of impurity. However, if you take a look at the leaf node on the right, then we're able to see that actually most of the class belongs to class 0. So this suggests that this leaf node is highly homogeneous and has low degree of impurity. Okay, let me see, right? Okay, any questions so far to talk about this homogeneous before I move into like how do we determine the degree of impurity? Yeah. Okay, so I think everybody understands like homogeneous is like sort of a fancy word just to say that we want the leaf class to have to be of the same class, right? Fancy word but useful word. Okay, yeah. Okay, so now if you take a look at the measure of node impurity, right, we have 3 different kinds: Gini index, entropy, and classification error, right? For the purpose of this micro workshop, we will simply focus on Gini index, which is one way to determine the node impurity, right? Okay, so the measure of impurity that we use here is the Gini index, right? So Gini index can actually be considered, essentially we are just subtracting, right, the sum of squared probability, right, from 1, right? Sum of squared class probability from 1. That's the idea. Okay, the general idea here is that when you square it, right? Personally, I'm a person who look at numerical value more, right? So I think you can see my spotlight, right? Right. So if I were to do example, right? If let's say the probability of okay, I'll go to the next class and talk about it. Yeah, but the idea is if a class belongs to if the leaf node is pure, right? Which is all the records in that leaf node belongs to one class, right? Belongs to one class, right? Then we will know that the probability of that one class will be 1, and everything else will be 0. Am I right? If we go by this idea, 1 squared is 1, 0 squared is 0. So at the end of the day, the summation of this will be 1 minus 1, right? This the Gini index will say that the impurity measure of the leaf node is actually 0, which is the minimum, right? All the records belongs to one class, right? However, right, if we look at the maximum, which is okay, so if you go through like the math and stuff, right, then at the end of the day, the equation that you get will be 1 minus 1 over the number of classes, right? So in this case, if we do H split, which is hateful or not hateful, right, it will be 1 minus 1 over 2, which is 1 minus half, which is the maximum value that you can actually obtain will be half. And this what this means is just that the records are equally distributed amongst all classes, right? So if I take a look back here, 50-50, right? we have equal distribution of classes within the leaf node. Yeah. So that's the maximum value we can get for this Gini index. So the idea here is we want to get a low a Gini index as low as possible, right? Ideally 0, right? Means it's very pure, right? Okay. Okay. So now let's take a look at a new example, right? So in this example, before we do a splitting, same situation, right? Instead of class 0, class 1, we have people going fishing or not, right? And in this case, we have two features, right? Firstly, is we take a look at the weather. If the weather is sunny or not, or secondly, for those who have girlfriends, right? Then for those girls, right, boyfriend, right? So vice versa, okay. No gender bias, okay. So girlfriend or boyfriend busy, okay. So in this case, we can take a look at these two feature. We can look at the decision made based on these two features, right? So let's take a look, right? If we use the Gini index, can we actually evaluate which test condition is better, right? So if you take a look at the first condition, which is split by whether the weather is sunny, right? Okay, so first, before we do the splitting, like what I mentioned, if we take if we go by okay, let me go back 2 slides for you. Yeah, go by this. Okay, assume that I'm right. Okay, so go by this assumption that the maximum value you can get is 1/1/2 because it's half binary classification. So 0.5 is the maximum, right? If you take a look at this, right, we take 1 minus the probability of fish, basically the target class being fish, go fishing or yeah, then and square plus the probability of don't fish squared, right? We will get this, and this will equate to 1 minus 0.25 plus 0.25, right? And then the final value, which is the maximum value you will ever get for this binary classification task, 0.5. Okay. So next, if we go by the features making the split based on whether the weather is sunny or not, right? We can take a look at this. Okay, yeah. If we take a look at this, first we can see the probability of fish is 2/9, right? So in this case, so in this case we start the value in and we take the square, right? And the probability of don't fish is 7/9, and then we start in the value, right? Because the fact the idea here is that even though we split by sunny and the weather is indeed sunny, this leaf node is actually not very pure because as you can see, majority goes to don't fish, but there's 2 people who actually still fish, right? When the weather is sunny. So the Gini index given to this class is 0.3405. Subsequently, if you take a look at if it's not sunny, do you fish or not? We'll see that this is actually more of an equal distribution or equal separation, right, of the record, right, 50-50. Then we'll see that the Gini index actually approaches 0.5. Yeah. Okay. So I think it's the same math. So I'll just fast forward it, right? If you have any questions, just let me know. Then I can come back to this slide to explain this again. Right. But the idea here is we will split based on whether your girlfriend or boyfriend is busy, right? So now taking a look, right? This leaf node is actually very pure because all the record in this leaf node actually goes to fishing, right? So basically, when the girlfriend is busy, you have some spare time, then you go fish, right? Yeah. So the idea here is, if you use the Gini index formulation to calculate this, we actually get a Gini index of value 0.0. Okay, good. Then if we go by the other one, it's the same problem, right, as the previous one, right? Majority of the class votes for don't fish. However, 3 of the records actually goes for fishing, right? So in this case, the Gini index that we obtain for this specific leaf node is 0.355. Okay, so staying on this slide for a moment, first, any question? Okay, if there's no question, then the next question here is, okay, so now we are able to evaluate, the decision So if you don't mind, just go back, right? So now I'm able to I'm able to evaluate the purity of a node, right? The impurity, the purity of a node, based on the decision made for one leaf node, right? One leaf. But then leads to two leaf nodes. So, or push the idea of like the purity based on the decision. That's the okay. So when we actually make a decision, right, which is the decision node is P, right? We actually split into K partitions, right, or K leaf, K. And the quality of this is computed as a summation of the Gini index of the leaf node, right? But it's not just any summation. You take the weight, right? The weighted sum. Moving to the next means that you see, let's take a look at the right side, right? Right side is easier to explain first, right? If you take a look at the right side, the weighted sum, right, is that we know at this girlfriend busy decision node, right, we have a total of 20 records, right? And when we go by this feature, we have 7 records going to yes, then 13 records going to right. But this is only this Gini index or this impurity only applies to 7 of these records, right? So we will take 7 over 20 multiplied by the Gini index plus the 13 records that leads to this impurity, right? We will add it together, and then this will give us the Gini index for making for this decision, right? So 0.3. So if I were to make the decision that based on whether the girlfriend is busy or not, the Gini or the measure, right, that I will be obtained from for this will be 0.23, which is not bad, right? Because you must remember that at first it's 0.5. Now I reduce it to 0.23. It's good, right? Yeah, it's like 50% reduction. If you look at the left side, right, same thing, right? Then at the end of the day, based on this decision, which is that whether the weather sunny or not, the Gini index will the Gini index only drops from 0.5 to 0.43. So this is like a relatively weak performance or not a very good split per se, right? Compared to this lah, right? But of course, if let's say 0.43, if let's say if let's say the girlfriend is busy, right, and this one is 0.48, then of course sunny is better, right? So we always go for after making that decision, what will be the right 0.23 in this case. I'll set it right. Okay, so that's all about how to determine the best fit. Then now we have to talk about the last part already, right? Then we'll go to the hands-on session. Right, the last part here is how do we actually determine when to stop splitting the trees, right? Okay, I'm sure you guys have spotted like once I make a decision, and in this case like once I make a decision here, like if the girlfriend is busy, yes, then obviously there's all the classes here belongs to the same class. I mean, all the records here belongs to the same class. Then obviously we don't have to continue, right? It's really pure. We don't have to continue for this business, right? So yeah, you guys should have spot this as well. So yeah, we stop expanding a node when all the records belong to the same class, right? Secondly, is we also can consider that we stop expanding a node when all the records have similar attributes. So what this means, right, is that if let's say I make a certain decision earlier on, then now, so I made a lot of decisions already. Then now I left the final 3 variables, right, to make a decision on. However, no matter how you split by these 3 variables, it always gives you 0.5, right? Like it's always an equal Gini index, right? So is there really purpose to actually to expand the node further? Yeah. So this is the other way to like terminate the induction of a tree. Okay. Another possible way right, is that we can do early termination, which is by pruning, or we also can determine, the depth of the tree, right? So, okay, I'll be, yeah, it's a bit far, but the depth of the tree is like, if you look at the Pokemon Go example, the depth of the tree is actually 3, right? Like three decision being made, depth equals to 3. We can actually make the model or tell the model, I don't want you to exhaust all the variables. I only want you to make at most 2 decisions. Yeah, you can even ask it to make at most 1 decision, but 1 decision, I don't think you'll get any. You won't get a good classification model. Yeah. Okay. So the pros and cons of a decision tree is as follows, right? First of all, decision tree is a if else tree, right? Like it's based on certain condition. If you fulfill the condition, you move down, right? So it's simple to understand, interpret, and visualize. Decision tree can handle both categorical and numerical data, right? It's extremely fast, right? I mean, no doubt, right? Because you just doing an if else tree, right? If you are lucky, the first decision is settled, right? Even if you're unlucky, it just goes down like by n feature, right? Then yeah, the accuracy. Okay, so this is relatively true. Like I mean, deep learning is a new thing, right? So but if you look at like decision tree and random forest, actually while they are not like while they cannot outperform deep learning models, in most cases, most cases, okay, they are actually having comparable performance, right? And it's not too bad, right? Maybe like deep learning 0.85, then decision tree or random forest can get like 0.8. Yeah, somewhere along those lines. Yeah. Okay. Then the pro is also the non-linear relationship does not affect the performance, right? Because as you can see, we make a decision for each feature in the feature will actually this relationship this decision. Yeah. Thing, right? Then secondly, it's unstable because a small variation in the data results in the data can actually result in completely different tree generated, right? As we can see, as we saw earlier on, just by selecting another feature, you can actually generate a totally different tree. Yeah. Then lastly, the greedy algorithm does not guarantee globally optimal trees, right? Same as the second one, right? Like a different tree, right, doesn't mean that all of them are globally optimal. They could be locally optimal. Yeah. Okay, then that's all for the presentation on the decision tree side of the house, right? Then now I'll move on into the hands-on session using the Jupyter notebook, right? So what I'll do now is I will actually send out the repository link. I'll send out through this Zoom chat first, right? So I'll send out the repository link through this Zoom chat. Then I'll need you guys to actually start clone to your computer, right? Or download it through the link. Then we'll resume the session at 11:30. 11:27. 11:30 is fine, I think. If you guys got any question regarding the slides or any details that I've gone through about decision tree, feel free to like ping now or ask me offline. Yeah. Right, right. I am receiving message. You guys can hear me, right? I hope so. Yeah, I'm receiving message that people can't access the link. Uh, let me see whether I can make it public. It could be a problem with the setting. Roy, I think I need your help to set it to public. Yeah. The project visibility. Is Roy there? Right. Uh, Actually, let me ask Roy for a while. Okay, I tell you guys what, right? Maybe I think Roy may be a bit busy, right? I'm not getting a response. What I'll do is I will actually set out a Google Drive folder, right? Then I'll send the link to the group chat, right? Then yeah, I think these repository issues will have to be sorted out again, right? Because we expect not really expect, we are hoping some of you guys, right, can work on some of the hands-on projects, right? For your experience with us. Give me a moment. Anyway, I think Naomi, you can assess is because you're working on the rumor detection project, right? The data crawling inside of the house, right? Then I think because you're working with code base, then you have the access to repository. Yeah, to our group repository. Okay, I have sent the link to the group chat, so perhaps you guys can see it now. If you guys the not sure if you can download. I think you guys can, right? Yeah. Yep, no problem. Yeah. So maybe I will. Okay, so for those with the there's no problem with the notebook, right? Because I uploaded it, but yeah, on my side there's no problem, but I'm not sure whether. So you guys should be able to see all this information, right? Like yeah, like all these images should be working fine for you guys. Yeah. Right. Yeah. Okay, I highly recommend you open in Jupyter Notebook, not Jupyter Lab, because I realized if you open in Jupyter Lab, the formatting actually goes a bit haywire. Okay, so for those who have downloaded the notebook, I need your help to over the next like 5 minutes or so, right? To actually go and download this data set from this link. I have provided a link here, right? Then next, I will need you to actually let me see what I can see here. Okay, I will need you to actually create this folder called dataset. Then extract all the files you downloaded into that folder. It should look like this. Yeah. I'm going to freeze the screen here. Okay. Yeah. Then okay, sorry. On top of that, right? On top of that, I need you guys to run this cell, right? Because this cell will ask you to actually start downloading two really small things, like really, right? Stockbirds and WordNet. Yeah. Let me see how can I do this. Can I do it this way? Okay, so I need to do this and this. Okay, so I shall go the other way around, right? Who is still downloading the files? And like be it the Python packages or the files, right? If you are, just use some sort of emoji. Gabriel is giving the clap, but I don't know, is it he just pressed it yeah. Yeah, but use some kind of emoji if you are still downloading the files, right? So that I can hold on and wait for you. Yeah. Anyway, this part of the class or the workshop will be actually more interactive. Okay, got it. I see the two of you. Yeah. It will be a bit more interactive and more hands-on, right? More, yeah, more actually, like more actually, you are actually handling the data more. Okay. Yeah. While we're waiting like one or two people to be ready, right? I realized, yeah, to check whether you got it properly set out, right? Just make sure you see this, right? Like this part, right? Is downloaded and then it displays true. Then the second part is try to run this cell, right? This the cell right below it, right? This cell will tell you actually what is if you have the data in the right directory and everything, it should display the data frame. Just leave it here. Disha is still downloading. Okay, great. Okay, then maybe I'll begin, right? Hopefully I can end this by 12:30. We can definitely drag longer, right? Honestly, I'm not sure how long it will take, but I will try to end by 12:30, right? Then I'll open to questions or any help that you guys need. Okay. Okay. So first of all, okay, actually, before we start on this, right? Just want to point out the fact that why okay, so decision tree, all these are quite simple machine learning techniques, right? And the reason why we decide to use decision tree, because we find that at first even in NLP stuff, right, decision tree is quite useful to solve certain problems, right? Especially like spam classification. One moment, yeah. Yeah. So sorry, back to the topic, right? So yeah, decision tree is very useful for simple NLP problems like spam classification, right? So that's why we want to go through that. And decision tree has like rather high practical value, right, in terms of the industry, right? Due to its ability to actually visualize the tree, interpret the results, and yeah, like easy to visualize and interpret the result. Yeah. And of course, comparable performance. Yeah. Okay. Okay, so let's begin. Okay, so this is the last part of today's micro workshop, where we'll be focusing on doing or performing sentiment analysis or sentiment classification using decision tree, right? We'll elaborate more about like this idea of sentiment classification in a short while. So yeah, the goal of this Jupyter notebook, or essentially the entire workshop, is to first to get you to familiarize with right, with some of the popular Python libraries that is useful for developing a machine learning solution, right? So first, we have NumPy, right? I think, okay, if you decide to take the data analyst or data route, you definitely use these three tools in your life. Okay, so the first tool is NumPy, which is programmed to do a lot of the linear algebra, right? So NumPy actually stands for numerical Python, like numerical Python. That's why it's called NumPy. Okay. Then next we have scikit-learn, sklearn, right, which is a popular machine learning toolkit, right, for Python, and it contains all common machine algorithms and extension. Then lastly, we have matplotlib, right? If you go even higher level, you can go for Seaborn, right? That's another visualization tool, right? The idea is this allows you to visualize a graph or visualize a graph, like it depends, right? Like visualize a lot of things. You can visualize heat map, what's that, bar plot, right? Like plot the bar cover plot, yeah, I think so. Box plot, sorry, box plot. Then all sort of different kind of charts, right? So for you to actually analyze the interaction between variables, or look at it, or look at your visual perspective. Okay. Then following, we hope that through this Jupyter notebook, you'll be familiarized with basic techniques for cleaning word level, right? I'll emphasize word level, textual information, right? So this includes like removing lexicons and domain-specific attributes. For example, sorry. Then reducing the number of words in the vocabulary, right? Such as like stemming and lemmatizing. Then be familiarized with basic techniques, right, for encoding textual features. The term for this, I will update the goals, right? The term for this is bag of words, right? The technique is called bag of words, right? And under bag of words, there's two common approaches, right? Which is firstly we use the term frequency, the less popular one, right? Then we have the term frequency inverse document frequency, right? We'll explain what that again later. And this is the more popular one. Yeah, then we'll implement decision tree in scikit-learn, and then we will visualize the decision surface and performance of learned models. Okay. Okay. So first of all, I think data exploration. Let me just talk about the data set in a very short, in a few minutes, right? So the data set that I've selected here is 140, right? The link set has been provided here. This is a relatively old data set, right? However, I think it's quite appropriate because firstly, this data set is first of all from social media, it's social tweets, right? So usually when we deal with textual information, especially in the social media, it tends to be dirty and tends to right. So this will actually give you a better sense of how information can be like hard to deal with or difficult to deal with. Yeah. Okay, so in the data set, we have 6 variables. Honestly, I'm going to use 2 only, but just to give you a highlight of what this data set comprises of. So we have the target, which is whether is it negative, neutral, or positive, right? Then, however, I'm not going to use the neutral at all. So we are doing a negative or positive classification. The idea of the tweet is not useful for us, not required for us. Date of the tweet also not required for us. We have the flag. Basically, the flag just means that what was the query being used to data set. right? We are also not using this. And see the user also not using, right? So the only useful information that we're using is the text information, which is the content of the tweet, and the target, which is the polarity of the tweet, right? Is it positive or negative? Right. Okay. Okay. So first of all, presented to us, right? So we can start off first, right? When we first get the data, right? When we first get it, we can always take like to have a brief look of how the data set look like. Technically, you should have done it prior to loading the data, right? The fact that you can load the data means you roughly know how the data should look like. Right? Okay. The other way you can do is you can look at. Sorry, I didn't run the cell. Okay. Yeah, then you can look at like the info here, right? So, I'm not going to go too in depth in terms of like the exploratory data. And using the data.info, you're able to see right column how many values there, now values, right? So things you see. Also be useful, right? Especially this part here can be useful when you are dealing with uncertainty, right? For example, if you are familiar with the Titanic dataset, it's also very old. The Titanic dataset is a dataset that has, yeah, just you can see it. Okay. Okay. So while I'm on this, one more hole. Sometimes, right? Not use the now. For example, right? Text here does not exist, right? And the value is now. Okay, so there's no text for this record. However, right, sometimes some people, because the way like programming works or the way you save the data, you save the data differently, right? The value here might not be now. The word here might be like non or something else, which is actually detected as a valid value, right? So sometimes you have to be a bit, right? It's this, but if you think something is going wrong, or you suspect that like cannot be that every record has this value, then maybe you a further investigate on whether is it a noun value. Yeah. Okay, one moment. Then yeah. Then next we can move into the describe view. So using the describe view, you'll be able to describe like the data type, which is mostly the numerical data type. It can tell you like the statistical measure, right, which is the count, the mean, the standard deviation, so on and so forth. Okay, so at the end of the day, like what I mentioned, I will only be using the text in the target, right? So, oh, sorry, I realized I should execute the cell as I go. Okay, let's do this. Okay, so in this case, right, 1.6 million records, it's going to take quite a while for you to train on your machine. So what we'll do is we'll only sample 10K records, right? I set the random seed and here, right, so that we can get like the same result. So it's just the random seed always use is 132022, right? Okay. So yeah, so same thing. This is I done here. Okay. Okay, so now that we said a rough what the data set look like and what we are dealing with, so let's go for a quick review or recap, right? Handling variables in machine learning, right? I call it structured for a specific reason. And we'll talk more about it. So variables can typically be categorized into two main categories, right? Numerical and categorical variables. And under variable, okay. So in most machine learning data sets, right? the data set that you get are actually mostly structured or like tabular, right? Kaggle.com. I can just go on Kaggle.com for now. Just a few. Yeah. I'm lagging. I'm actually lagging. No. So. Okay, if you go to like competitions, right? If let's say you go to some of the data sets, right? Let's take a look at like let's see. Okay. I mentioned about, but it's more straightforward to me now. So let me open this data set. I think we are able to see a preview of the data set without signing up for the competition. Yeah. So looking at the data set, we're able to see that the data are categorized, right, or put into a table format. Okay. Yeah. Okay. Yeah. So we can see like they are put into formats, right? Yeah, proper formats. So most of the machine learning problems out there that when you do deal with, right, are mostly structured, and then they can be categorized into like qualitative and quantitative data set, right? So numerical values are quantitative data set, right, which is they describe like a measurable quantity, right? So for this case, right, like for continuous, you will ask the question like, can I measure it, right? So like, can I measure, for example, the length of a table, right? That's a continuous value, right? So the height of someone. Therefore, discrete variable is more about counting, right? For example, the number of family members in your household, right? That's like a counting question, right? Or how many pets do you have? Therefore, categorical features or variables, they are more of qualitative data, right? And they are more of like what type language category, right? For example, nominal values, right? So in terms of nominal values, you can ask things like what's your gender, right? It's usually like quite nominal, like there's a fixed range of value that you can choose, and each of the value does not have superiority or order, right? Like it's not, male is not more superior than female, so on and so forth, right? Then we have values like ordinal values, right? Ordinal values, we can look at things like, let's say, academic grades, right? That's one thing, like A, B, C, D, right? That's the order, right? Like A is the best, then B, then C, then D, so on and so forth. So that's one thing we can do. Ordinal values also got like sizes, right? Like shirt size, small, medium, large, right? Small is medium is definitely bigger than small. Large is definitely bigger than medium, right? There's a relationship between the categorical features. Yeah. So yeah, I give a more in-depth explanation here, right? Yeah, if we just look at purely the Titanic data set, like purely Titanic data set, continuous variable, okay, we have the variable age, right? Yeah, sorry. Okay, we have the variable age. Then for this variable, we have things like the number of siblings aboard the Titanic, and number of parents and children aboard the Titanic, right? Okay, therefore, this kind of numerical values, what we actually perform is we actually to perform something called feature normalization or feature standardization. Right? It depends on how you want to do it. Right? The general idea is that first, when we, yeah, okay. So first of all, right, if you take a look at since I'm on it, right, let me take a look at this. Okay, I think there's a way. Okay, this is something good about Kaggle, sort of. If you look at, I think the column view, right? We can see that, we know age and fair is continuous value, right? So if you take a look, right, you look at this, fair has a minimum value, okay, has a mean value of 32.2, right? I remember I saw a max on before. All right, the max is here, right? The max value is 512, right? Then the minimum 0, okay, probably missing data, right? but the idea is Ming 32.2 and then max of 512. You cannot go on board of a ship for free, okay? Especially Titanic. Yeah, then if we look at the age, then we will have values, the mean values being 29.7, the max value is only 80, right? So if you just look at, the way linear regression works is that using my listing for a while, right? We'll have a coefficient, right? So in this case, let me call it beta 1, W1, right? Then it will be beta 1, W1 plus beta 2, W2. So in this case, we are X1, sorry, I use W here. Yeah. So weight 1, X1, weight 2, X2. Let's ignore the bias term for now. Right, let's ignore. The idea here is that, if you do this, X1 being the age and X2 being the fair, right? We know that fair has generally a higher spread of values, right? It can spread all the way to 500, 500 something, 500 plus values, right? So it means that this weight here, or the entire line is strongly dependent on X2, right? There's a high dependent on how X2 actually fluctuates, right? If X2 is suddenly 510, then no matter what X1 is, even if it's 80, the 510 is going to outweigh X1. Yeah, very likely outweigh W1 and X1 together, right? So this is what we know as like variables of different scale, right? Yeah. So another example is like height and age, right? Your age typically is between 1 to 90, okay, 100, okay, 100, 1 to 100. Then your height for males would be like 150 to 180, 190, right, about there. So yeah, so generally like continuous values are placed on different scale. And then if you do linear regression that way, it's very likely that one variable will outweigh another variable, right? So we'll do something called normalization and standardization to ensure that the variables are placed on the same scale. Okay, so we use a technique, right? So we put the different variables on the same scale to one. There's normalization. I'm not sure whether you guys have really learned this, right? But this is somewhat not the main focus of natural language. So I'm not planning to dive too much into normalization and standardization. So this is just to give you like a brief introduction to like, what are the things that you should actually perform. Okay, so yeah, so two of the common standardization techniques is min-max scalar and standard scalar. Okay, if you have any questions regarding like the skill, like future scaling or anything, just feel free to ask any of us. Yeah, I think it should be helpful. Okay, then next we'll look at the qualitative data, right? So like what I say, P-class ordinal, right? A bit do, right? Sure, first class better than second class better than second class, right? So that we have right. So using the cabin, we can actually get which deck does the passenger reside on, right? Is it the lower deck, the middle deck, or the higher deck? Right? In this case, there's actually more, but now for the purpose of demonstration, I classify into low, medium, high. So for ordinal encoding, we can encode in this way, which is that the one having a higher value, right? If we go by shirt sizes, the first one will be small, medium, then large. Okay. Then next, for ordinal value, for nominal value, for one hot encoding. So one live on lower deck, so he will have a vector value, or he will have the following value, right? If you want to be more precise, we can do something like this: deck low, deck medium. Let's see. Okay, and deck high. Okay, so that's the idea, right? So passenger one is 2 medium deck, and then passenger 3 is high deck. So this is like the basic techniques for how to manipulate structured data. Yeah. Okay, I'll move on into how do we handle text variables in machine learning. Okay, so this is unstructured, obviously, right? Yeah, is why I bring out the point that common data points or data variables are structured. Okay, so we have two main kinds of data: structured data and unstructured. Right, structured data are what we saw just now, and they are usually stored in. Then unstructured data are more common nowadays, right? Images from like CCTVs, cameras, videos, right? Text, audio, video, documents, yeah, common. Okay, so how is textual data actually different from the types? Right, firstly, the biggest difference is that common variables are, okay, let's say structured, right? Each variable is assigned to an appropriate header, right? So if I say that this is the cabin, then the variable contained within the cabin should correspond to it, right? You cannot suddenly have an egg, the cabin. Okay, so they usually have the following characteristics. Firstly, because these variables, right? For example, let's say you have a table, a database, right, containing the concerts that's going on, right? Then usually the concerts you will have like which band is organizing a concert, so on and so forth. All of these are laid down by the principal, right? You're operating rental service, for example, rental for concert, right? The venue rental for concert. So generally you have like a guideline, like what is the purpose for this rental, who is renting it, how many days they require it, how much are they paying, so on and so forth. Right? Then these data are usually relational, like they are very structured, right? So we will store them in relational database, right? Which actually fulfills the 4 properties for transaction. Safe properties, right? Atomicity, consistency, isolation, and durability, right? Don't worry too much about this. The idea is just to let you know like where the data set are typically being kept, right? Then in comparison, textual data are unstructured qualitative data, right? Qualitative, right? We'll talk about it why. Then this data set actually has the opposite characteristics, right? You cannot predefine the data model because, for example, if I want you to write, very easy. If I ask every one of you to write a review about your Euro internship, right? It cannot be that Ming Shan must appear in every single one of the review. It cannot be that Ziqiang must appear in every single one of the review. Like people from my team might not even know who is Ziqiang, right? So like that's why it's very unstructured, right? You don't know which are the comments pointing towards who, right? Unless you do some kind of like, heuristic, or you go and control F Ming Shan, control F Ziqiang, that kind of stuff, right? Yeah. Then they are usually stored in NoSQL. The reason is because it's more scalable and it's actually more efficient to store and retrieve these unstructured files. Okay. Yeah. So firstly, okay, textual data are considered qualitative. Like why, right? I thought qualitative is categorical and nominal values, right? Okay, the reason is because these textual data are actually describing, right, qualities and characteristics of a data unit, right? So for example, looking at this review here, right, we can see that it's actually describing the quality of the room, and it's also describing the attitude or the friendliness of the staff, right? So it's actually providing some kind of quality or characteristics of something, right? And then this unstructured qualitative data are actually critical to business and public organization, right? In the sense that first, it allows business, right, to rely on the reviews, right? So for example, in this case, I see this, then I'll be like, okay, who is that staff, right? I'll be very interested, or I'll pay more attention to like, how is my staff actually behaving to their customers, right? Is there a need for me to actually intervene and actually make the customer service better, right? Then for public organization, it allows them to react to early like hateful rumors, right? If, for example, nowadays like COVID-19, some people will start spreading like COVID-19 killed someone, or someone suffering for COVID-19, like things that is not. I mean, it's a rumor, lah, right? It's not disclosed by the government, but it's also not acknowledged by the government, right? So these are things that we need to be careful of, right? Even nowadays we have the OCBC transaction, right? It is, yeah, it's quite, the world is quite strange now. So yeah, so subtly under the research of text mining and information retrieval, right, we have like many subfields working on extracting meaningful data, right? First of all, the first one we have is name entity recognition, right? For instance, given a tweet, we want to extract information, right? Such as given this tweet, right, we want to extract like who is the person within the tweet, right, in question, right? In this case will be. Then sentiment analysis will be that, you know, given in my life, on the rest, then suddenly just one forever behind, right? Like it's a sudden pause. Then we can actually determine like the polarity of the tweet, right? Is it negative, positive? Possible like suicidal or not suicidal, right? Then after we can look at aspect mining, right? This is like, opinion mining is a combination, right? Aspect mining is we know that this is a review of let's say a hotel, right? So the aspect of a hotel would the aspect of a hotel we are expecting would be how is the room, how is the staff, right? So these are the aspect of what we look in at a hotel, right? So in this case, I give an example like the battery life on the latest Google Nexus 6 is pitiful. Okay, in case you guys don't know, the Google Nexus 6, although it's very powerful, but it only like gives like 4 to 5 hours of battery life, which is I think quite insane. 4 to 5 hours only. Yeah. Okay. So we'll extract like battery life. Right. And then if we combine together with sentiment analysis, we can say that it's battery life and it's a negative sentiment. Yeah. So aspect mining can be combined with sentiment analysis. Okay. So far, I think it should be no problem. I'll continue further. Okay. So challenges by textual data, right? Firstly, that machine does understand languages, right? All from ICD or mostly from ICD here. So or we have worked with programs, right? So we know that machines work with binary code or they work with numerical values, right? So they cannot understand languages or raw text. So we actually need to convert these input features or this language into numerical format. Secondly, machine learning models, right? The easiest way, linear regression, right? Given x1 to x3, you plot a graph. Then suddenly now I give you a x4, x5. What do you expect the linear regression to do? Right? The linear regression cannot do anything about it. Right? The most it can do is you drop the features. Yeah. Then thirdly is the sequence that the word appears in actually matters. Right? So in this case, right, I just give a simple example, right? 3 words, same words, right? Putting in different orders can result in different can give a different meaning, right? Yeah. So first, this is interesting. It's a comment. Then if I swap the first 2 words, it becomes is this interesting, right? It totally changed it. It changed from a comment to a question, right? So lastly, language and grammatical rules, right? So we have like a sentence, not always, but would sometimes or very occasionally contains things like noun modifiers, prepositions, determiners, and etc. Right? Okay, then just a note, like this list is not exhaustive, right? There's actually a lot more or many other more reasons, right, for why text modeling is difficult. Okay. Okay. Sorry, just bear with me one last part, then we'll go into the stress exercises, right? So for common characteristics in textual data, like why is it so tough, right? Why? Okay. So to facilitate the discussion here, we'll use the following tweet as an example, right? So this is the tweet. I copied from Google AI. I made 2 modifications. Okay, but yeah, one moment. Okay, yeah. Okay, so first of all, we have stop words, right? Stop words are common words and they are automatically omit by search engine, right? Because they don't serve much meaning. right? It's grammatically correct for us, and it makes sense to have that word in, but it doesn't describe what is going on, right? So such things as the, and, right? It doesn't provide any meaning. We have contraction, right? Sorry. We have contraction. In this case, like today we have present, right? So we have become we have, right? Then punctuations. So these are punctuation based on string dot. Okay, let me just run this. So we can run this next cell, which is string dot punctuation, right? We'll see examples later. So sorry, there's no S. Okay, yeah. So we can see this. Then we also can see that in a tweet we can have sometimes URLs. Then we have mentions like at Google. Not here, but sometimes you can have it. Then we can have hashtag like ML or NLP, right? Then we have to tokenize it, right, from a sentence to word level. Yeah. Okay, so 3 mini exercises that I'm going through here. Then I will get you guys to do something, right? Okay, first of all, we'll remove contraction, right? Thankfully enough, there's a package literally called contractions, right? You literally just go and Google Python contraction, you can find it. Okay. So you can try to run this example. I suspect some of you will run into a problem where contractions is not found, the library is not found, right? So what I need you guys to do is just go and Google Python contractions, and then you'll find the library that you need. Yeah, then you just do a pip install. Okay. Let me know whether you guys can get this output. Yeah. Let me put the stop watch here. Okay. So yeah, I'll wait probably like 1 to 2 minutes. Right. It's a fast installation. Okay, if you need a command is pip install contraction, I think. Let me double check. Yeah. Okay, so this is the okay, then next maybe I just move on, right? Because yeah. Let me know if you need some time later. Yeah. Okay. Next we'll move on to removing punctuation, right? Like exclamation mark, question mark, technically doesn't serve much purpose for word level handling, right? So if you do this, what we do is we iterate through the punctuations, which is here. Then we replace each of the punctuation with an empty string, right? Then we'll get this, right? Technically we remove the curly brace. This is tilde, right? No, this is just a wave, I guess. Yeah. Then we also remove the I hyphen M, right? The hyphen is removed. The din also got removed, right? Yeah. So we remove all sort of punctuation here. Then lastly, we'll go into removing stop words. Oh, sorry. Which part do you have problem with, Jashan?
The pip install part.
Pip install part, you have problem with it.
During installing, it showed a lot of error code. We say that the need Microsoft Visual C++ 14.0.
I see. Can Daniel or like Daniel, Rabu or Zishan, can you go and can one of you go and help Jashan with it? Yeah. Actually, maybe just you hold on for a while. Actually, just hold on for a while. Once I go through this part, you'll go. They'll go and proceed to do their there's a small mini hands-on. Yeah.
Yeah, no problem. Thank you.
Yeah. So the last part here is we remove the stop words, right? So same thing. We iterate through the sentence here. Then we check whether the word is in the stop words. If the word is not inside the stop words, right? I mean, if it's the stop, okay, see. So this condition is if the word is inside the stop word, we will skip, right? We'll go to the next word. If not, we'll add it into the clean text, right? Something interesting to note, right, is that, I-M, if you do a contraction first, right, you will actually change it, right? See, it become I, okay? Yeah. So I sort of answered my own question. Okay. Yeah, so does the order of the future preprocessing matters, right? The answer is actually it matters, right? Because if we do the punctuation first, we'll actually see that the word din will have the hyphen removed. Then when you perform the stop word removal, it actually won't remove it because it didn't see this word before. This word doesn't exist in the vocabulary. Yeah. So sometimes the order that you clean the textual information matters. Yeah. So don't think that you can just do in any order that you want. Yeah. Okay, so next, okay, I'll go through this one. Then, perhaps I'll need you guys to go and try to do some cleaning yourself. You can copy and paste the code on top, right? But there's still some things that you have to make adjustment for. Okay, so first of all, we'll do. Okay, so we'll do for the first case, right? We are doing like a regular expression to remove the HTTPS regular expression, right? So that's the first step. The second step here is we are removing mentions, right? So in this case, we highlighted that anything with a @ sign will be replaced with a single with an empty string, right? This is regular expression, so it's okay. The easiest way to explain regular expression is that it's pattern matching. Okay, so using regular expression, you can do pattern matching so that when a specific pattern is matched within the text, then it can perform some kind of like substitution or removal. Yeah. You can even extract specific patterns from the data. Okay. Yeah, so that's the idea. So maybe I can get you guys to do the necessary feature cleaning here first. Yeah. Let's take about, we don't have much time. Let's take 5 minutes, right? 5 minutes. Then I'll show my answers, then we can continue. Feel free to sound out if you have any questions or any problems. Okay, maybe like for the purpose of time, maybe I can just go through the steps that I take, right? And like logical steps that I take first, right? So if we just go by the fact that we need to do all the things that we mentioned on top, and we need to do it in specific orders, right? What we can do is we can first actually is simply on this order, right? Simply this order is fine. Yeah. So first of all, we fix the contraction first, right? So in this case, we copy and paste. Rather than doing this, we just do data equals to contraction data. So this is to fix the contraction. Right? Yeah. Okay. Then next is we need to remove the punctuation, right? So we can just copy this. And in this case, everything remains the same. The only thing we need to do is just to change this to data. Okay, so let me just put words here. Okay, then this is a punctuation fix or removal. Okay. Then the last part here is to do the stop words, right? Okay, but in this case, I'm not going to do the stop words, but you can do it, right? Just it's fine to skip not do it here first for now. So we actually see that we actually clean the data. Actually, this guy is very clean. Let me see. Okay, so this one got the add mention, right? So let's see. Right, then we are able to remove the add mention. We're able to remove certain stuff, right? However, you see there are still things that's unclean, right? Even though you remove the punctuation, this doesn't make sense. So maybe you need to have another rule to specifically remove these quotations, right? So these are small things that you need to like slowly fix, I guess, right? Then it becomes like a habit. Yeah. Yes. For me, I'm just going to do it once, right? It's easy. It doesn't take too much time. Okay. Yeah. So now we have the quotation removed, right? Okay. So, however, right, are we really done? Right. That's the question that you might want to ask. Right. So you might want to pick like maybe 10 samples to take a look whether your cleaning is up to the standard that you want. Right. Even just by picking a random one just now, I already found that something was not clean. Right. Yeah. So in this case, if I were to choose this, I'll realize that you see the hashtag here is not being clean. Right. So, but this is regularized, this is regular expression. So it's going to be a bit tough. But the idea is you can just do this. Right. So you remove all this to a hash. Because the idea is this add sign, right? Yeah. Now if we do this, yeah, we can see that this is removed. Right. Okay, so that's the small exercise that I plan to have, but because of a bit of time constraint, yeah, some technical hiccup. So we just continue this way. Okay, so far any questions first regarding the data cleaning here? Maybe like short 1 to 2 minutes. Yeah. If you got any question, I can try to answer. Okay, if not, I'll proceed on. Okay, the next thing is this additional material, which I'm not doing in terms of our data cleaning, but it's something that you might want to know, right? It is a common technique for word level cleaning. Right. The idea is, if we are treating like this sentence into individual words, right? Individual words. Then technically all of these individual words have the same meaning, right? Change, changing, changes, change, changer. We'll go to change. Right? These are just different tense, right? Present tense, past tense, etc. Then there's two techniques, stemming and lemmatization. Okay. So the idea here is that because language has established grammatical rules, a document can actually contain like different forms of words, which is like driving, related words having the same meaning, like nation, national, and nationality. So to remove this like textual noise, we can use normalization technique like stemming and lemmatization. The idea here is using stemming, right? The idea is we simply chop off the end of the words, right? Which is like the suffix or prefix with the aim of achieving a normalization effect. However, right, if you simply chop off the end of the word, you can have two effects, overstemming and understemming, right? Overstemming means that if you use like universities, universal and universe, right? If you cut off the end too much, what happens is obviously these two words shares the same meaning, and then these two words share the same meaning. But what happens now is all four of these words share the same meaning. Universe, yeah, universe, right? Then we also have the idea of understanding, right? Data and this also like this is another word to represent data unit, right? So if we do a stemming on this, you actually get DAT, that, and then DATU, datu, right? Which is wrong also because these two words actually represent the same thing. Yeah. So to do a small showcase, we have this, right? You can see that if you do stemming, you can get the situation as described. Then if you do lemmatization, this is an organized and step-by-step procedure to actually obtain the root form of the word, right? Instead of just cutting off the ends, it actually makes use of vocabulary dictionary and morphology analysis. Okay, so essentially is you can think of it as like it's a more structured approach, like it's a more logical approach, right? Like because you're tracing it back. Output of this lemmatization, the output of the lemmatization, the root words, that's why it's called lemmatization. Okay, yeah, so another, okay. Yeah, that's so far for feature cleaning. Now I'll move into feature extraction and training of decision tree. Okay, so I think first of all, let me I realize I should have addressed this first. So maybe Joshua, you can just try to follow what I say. Then you try to do what you need to do. Because I don't think I will have time to cover the exercise in the workshop today. So the feature extraction will take a bit of time, and this is like the gist of the workshop, right? Like the biggest point that you should take away from the workshop. So and for this section, there's no hands-on. So maybe you just follow through. Then for the training of decision tree, can take it back. Then if you got any question, you can ask offline, or you can ask during the next session. So maybe the next workshop session, we can start a bit earlier. Like we'll open the slot earlier. So maybe like 30 minutes earlier. Then anyone got any question can come in and ask. Right? Or we can even go through, or I can even go through like how I do it. Right? Okay. So first, looking at the pair of words model, right? So the idea of looking at sentences at word level the idea of comes from the technique back of words. You literally can Google this. Okay, you can Google this. Back. Okay, the idea is that because textual data can be considered as qualitative data, right? The words of the document can actually represent categorical or nominal values. So what we can do here is we can actually do a map real value vectors, right? And then this technique is called back of words. Okay, so back is a representation, I said, right? That describe occurrence of words within a document, right? It consists of two things. Firstly is you need a vocabulary of known words, right? And then you need a measure for the existing vocabulary for known words could be that. For this example, I have 4 documents here, right? Like you can take it as 4 tweets, right? So each tweet is a document. So to construct this vocabulary, then what you can do is option 1, you can actually take the unique words, right? So basically, take the unique words within them. That's the first approach. The second approach is if you have some kind of rule or business principle, you can actually define vocabulary yourself, right? Then the third approach, which is the not recommended approach, you just take the entire dictionary, right? The entire dictionary by Oxford is 171K words, which is a lot of dimension. not a lot of dimension, but yeah, a lot of dimension. Okay. So this is the idea. So you need a vocabulary of known words. Then a measure of the presence of the known words, right? What this means is that, okay, so let's say you construct a vocabulary here, right? I can give you the value now. The vocab. I need to do this. Okay. Let me do this. Let me show you what I have. Okay, let me show here. I have another. Okay, so I can show you that the vocabulary here. No, man, something stuck somewhere. Here. Yeah, it is stuck somewhere. Sorry. I see. Okay, I got it now. So yeah, so if I take the unique words, like all the unique words across the 4 documents, I'll actually have 8. The vocabulary says to be 8, right? And these are the words, right? So what I will so we know that each document will be represented by a vector of 8, right? So there will be 8 values in for each document. However, we need to however, you see we have words, right, that can occur 2 times, right? For example, the word here, the, appears twice, right? The word sun here appeared twice. Yeah, I think those are the number, like the counting of the words, right? So we need a measure, right? Do we count them, or do we simply mark them as presence or absent, right? So that's the idea. Okay, so for the dummy approach, right? The dummy approach is, instead of using the common pair of words approach, we use one-hot encoding, right? Since it's categorical values, right? So in this case, we represent each sentence as a vector with each of the word representing 1 for present and 0 for absent. Okay. Okay, so I'll let you guys run through the code yourself. Okay, I want to show you. Yeah. You can come and ask if you have any questions. Okay. Then the idea here is, once we do that, you're able to see that each document is being represented by the count, right? Because this is the dummy approach, right? It's just that, so document 2 has the word bright, but it doesn't tell me how many words, like how many times bright appeared, right? It doesn't give me that information. Okay, so that's the problem. Okay, so now moving forward, right? Rather than looking at the presence of each word, right? This is very problematic, because if we do that, we actually effectively disregard the number of times each word is being mentioned in the document, right? And this frequency and the frequency of the word occurrence, right, actually gives very useful information, right? The intuition can follow this way, right? If the word occurs frequently in the document, then it just signifies that that word is more important and more relevant than all the other words that appeared fewer times, right? So if let's say a document keep talking about Disney World, right? Then this document is about Disney World. Yeah. Right. If you only have the presence, you don't get this information. So what we do is we can start with the calculation of term frequency. Right. I'll let you read this yourself, but I will explain the formulation here. Right. The idea here is just that the FT comma D here simply represents the frequency of word T within document D, right? Frequency of word T within document D over all the words in the document. It's just a normalization, right? So yeah, so in this case, right, if let's say we look at the first document, there's 4 words. If let's say there's no stop words or anything, right, let's say, so each of these words will be given 1/4, right, 0.25. Yeah. Yeah, it is that simple. Yeah. Okay. So I went through I'm using a package to help with this, because if you are able to do the exercise here, like manually, then you're good enough, right? We should use package to help us to do this better. Okay, so in this case, right, if you take a look at this, we do the term frequency factorizer, TF-IDF factorizer. We say that we don't want to use IDF. So if you take away the IDF, this is just a TF factorizer, term frequency factorizer. We get back the same vacuum, okay, not the same, because similar, right? The reason here is because the sun got W. Okay, let me remove the sun. Okay, yeah, it's 7 now. Okay, sorry. It's my cleaning not very well. Yeah, okay. Okay, so we get the same vocabulary size, then the same vocabulary, right? So now if we do a transformation, okay, we're going to see like, here we go, right? Document 1, after you remove all the stopwords and everything, it only contains 2 words, blue and sky, right? And each of these words is given 0.5. Document 2 is given the word bright, sun, and today, right? And each of the words is given 0.33. Okay. Yeah, I wanted to give an idea of this. This is a very high level idea. Okay. The idea is that when you do encoding and you do a transformation, you'll reach a matrix with a lot of zeros, right? And it's not effective to store so many zeros, right? Like this is just a 4x7 matrix. Imagine you have a 500 by 2000 matrix, and then 90% of it is 0, right? So it's not effective to store it with all the zeros, right? This is what we call dense matrix, right? So it's not good to store as dense matrix. So when you do a vectorizer transform, they actually store it within a sparse matrix or a compressed sparse row format. Yeah. Okay. The general idea is just that all the zeros are redundant. You don't have to store as 0. Okay. Yeah. You just need to store all these 0.5, 0.33 values. Okay. Okay, so that's it for term frequency, right? So term frequency makes sense, but what is IDF? What is inverse document frequency, right? The idea of inverse document frequency is that, okay, if let's say your current document talk about Disney World, but then right, all your other documents also talk about Disney World, right? Then the question to you or to the document would be that, is it, so like it could be, okay, firstly, it could be that the whole collection of documents comes from Disney World review, right? So there's no point in knowing that Disney World is the key topic. I know already, right? So the idea here is, given that information, can I actually lower the weightage for Disney World, right? So I know it's about Disney World, but I want to know what are they talking about Disney World, right? So in this case, we can have this thing called the inverse document frequency, and then it measures like how rare a term is across the corpus, okay, right? So the rarity of the word. The intuition here says, right, see, if the word appears too many times, then what will happen is appears too many times in the document and across other documents, then that word is probably not relevant or meaningful word. Yeah. So if you look at this formulation, the IDF goes by this way. And here, which I say, right, the total number of documents in the corpus is n equals to the norm of D, right? So the length of D, size of D. D is your corpus, right? D is your corpus. So number of documents, right? So assuming that D is, in our case, 4, right? So if I were to say the documents, number of documents is, total number of documents is 4 here. Okay, then the number of times the word Disney World, okay, let's go with the hypothetical scenario of Disney World. Okay, so assuming that Disney World appear across all documents, right? So this count, right, will say that, okay, Disney World appear in D1, Disney World appear in D2, D3, D4. So this is also 4. So it's 4 divided by 4. And then if you take the log of 4 divided by 4, it will give you 0. Right? So it's just giving a weight to the term frequency, because it's just giving a weight to that word to say that this word is actually overused. It's not useful at all, right? To determine whether to determine the topic or to determine the content of the document. Yeah. Okay. So that's from like a formulation perspective. I mean, like if you use numerical to take a look, that's how it works. Right? So inverse document frequency, right? Like inverse. Yeah. Okay, if we sorry, a bit out of time, I know, but document frequency, right? If you don't look at inverse, a normal document frequency will be just the inverse of this, right? The count will be on top, the n will be below, right? That's why we take the inverse. Then for the log, right? The log is because if you have a very large corpus, the IDF value will be very large. Yeah. So imagine I have 10,000 documents now, then only 10 of them contain Disney, right? Let's say Disney World. The value of the IDF will be 1,000, right? We have the same problem as the future, as the continuous variable, right? This value is too large, right? So if we take the log of this value, we actually reduce it significantly to 3, right? To a smaller range, to a smaller scale. It doesn't standardize it, but it scale it down to a manageable value. Okay. Okay. So now that we have the IDF, we can actually combine it. Right. That's the idea. Okay, for information, right? Like this is the general concept that I'm teaching you guys here, and it's also what I've been taught. But when you go and explore, look at how libraries implement these techniques, right? You can actually realize that they actually do like additional operation or additional steps. Okay, so for example, right, this is a standard notation, but in scikit-learn, what they do is they do additional thing called smoothing, right? So they add 1 to top and add 1 to bottom. Let's ignore the +1 behind. Okay, so what's the rationale of adding this smoothing, right? Just a very short one. The idea is that if let's say you have a predefined list of documents, vocabulary, right? And in your vocabulary, surprisingly, you have a very unique word, right? Let's say the word is medical, right? But then the word medical never appear in your corpus, right? In your training, there's no such word called medical, right? So what will happen is if you try to generate the IDF for medical, the frequency of medical will be 0, right? Then what will happen is you have this problem that you cannot divide any value by 0, right? There's a divide by 0 error. So the idea here is I add 1 to the bottom, right? To counter the to make it such that you divide by 1 instead, right? Then to counter this value, right, I add a 1 on top as well, yeah, to make it more fair, right? Yeah. If not, you have another situation that if you same situation, total number of n is 4, right? So 4 divided by, let's say 4 plus 1, right? So now you have a new problem that your log value now is negative, right? Because it's 4 divided by 5, right? So now you have a negative value instead. Yeah. So that's why you have to counter with a 1 on top for the numerical values. Okay. Yeah. The +1 is, if you're interested, we can talk in another discussion. But yeah, but just so you know, there's a lot of different formulation. Okay. So I can probably understand this, but I can understand the second one. But the other two, it will take me some time, right? Like, yeah, I need to go understand the intuition and the motivation for formulating it this way. Yeah. Right. So do take note that when you do TF-IDF using packages, you need to go and find out in details what it's actually doing and is it doing any additional operation. Yeah. I'm reaching the end already. For the decision tree, I'll leave it to you guys to implement. Then we can talk about it in the next session. Okay, so first of all, for the learning of vocabulary and IDF from the training data set, I have the code for you, same, right? So simply what I do is I remove use IDF equals to false. Technically, I should add L1 norm here. I should add L1 norm here. Okay. Then, so now, because I didn't, okay, so the previous thing that I omitted or I added is this, right? So now that I removed it, you can actually see that the IDF value is generated, right? Then we can see these are the IDF value. Okay. Then now we can look at the document frequency. Okay. And the reason why I say it's a playground, right? I didn't have the time. If you have the some time, you can go and play around with it. Give me a moment. I added in the other notebook, but not this notebook. Yeah, I didn't expect it would take so much longer. Okay. The playground is here, right? Yeah, so there's actually a range of things that you can do, right? By default, TF-IDF lowercase the sentences. You can pre-process the data if you want. So remember that we have a function called clean data on top. You can actually call it here. Clean text, I mean, sorry, yeah. You can ignore a tokenizer, ignore this for now, right? Then for stop words, right? That's why I didn't remove the stop words earlier. You can actually perform the stop word removal at this level, right? But do take note, you have to pass in like the stop words that you want to use. Okay. Then here's the stuff. Frequency range, meaning that what's your cutoff point, right? Then we have like other normalization and spoofing term, right? For beginners, I think, or for like novice, right? You can just try to use the first part here, right? Based on what I experiment around, I feel that max DF and min DF typically doesn't really change the performance much. Typically, yeah, typically, right? So it does, but not a great deal. Yeah. Okay. Yeah. So same thing, right? This is the playground. So next, I would like I think you guys will see this instead, right? Which is a bunch of empty stuff, right? So I have the headers for you guys. So maybe after this session, when you guys are free, even after the entire workshop, when you guys have some free time, you guys can go ahead and try this because it will be related to your hands-on project for the Europe if you're interested, right? So do try this out, then let us know if you face any problem. Ignore the results. So at the end of the day, I have this tree, so you can visualize it, right? It's very small because I never zoom in and everything, right? This tree has a depth of 1, 2, 3, 4, 5, 6, 7, 10, 11, 12. These are three, that's all, right? No, actually not very deep, it's okay. Okay, yeah, so that's that you can actually visualize decision tree. If you are interested in presentation, okay, to see what flows your book. Okay, so I want to wrap off this session as well because we're running out of time, right? And we already we already spent like 4 hours on this. We're going to drag beyond 1 o'clock. Okay, so what's next, right? Is that once I hope you guys can actually I just need the last 5 minutes. Anybody got questions regarding the surf frequency and the inverse document frequency? Yeah. Anyone? Yeah. Okay. If not, right? Okay. Although TF-IDF and everything, the technique is good, right? However, there are some shortcomings that we have to address, right? Firstly, is we have to design the vocabulary very strategically, right? Because we need to make sure the size is maintainable and the dimension is not too high. Then secondly, the sparsity, right, is going to be hard to model, right? As you can see just now, the example is what you have a 2,000 by 40,000 matrix, something like that, right? Right. It's just a very large matrix. And then within the matrix, 90% of them is 0, right? That's one. Then number 2 is even if we have a compact format to store the data, like what I say, the compressed sparse rows, right? It's still very tough for the model to learn meaningful information because there's so many zeros. Right? Yeah. Then lastly is meaning, right? The meaning in the sense that like what I mentioned, right? the lemmatization and the stemming, right? Because we treat each sentence or each document, right? Okay, I didn't bring this up, but each document is the reason why it's called bag of words, right? Is because we treat each document as a collection or as a bag of individual words, right? So we don't care about the sequence, right? We treat it something like, you know, variables being like IID, right? Individual and independently uh, uh, independent and identically distributed, right? Like that's the idea that we treat it with. Yeah, so the idea here is but the meaning does have purpose, like what I mentioned, the example that I gave, right? So context and meaning can actually offer a lot more to the classification model, right? And the best result that I get for this decision tree is 0.65 if you're interested, 0.65, right? So it's actually quite low. Okay. So hopefully what we want to do is in the upcoming workshop, they'll be going through potentially the same data set or new data set, right? Then they'll be going through a newer embedding technique based on deep learning, right? Then the newer embedding technique, word embeddings, right, will actually address the shortcomings of BOW, pair of words efficiently, right? It's able to model like the meaning and the sequence of words more effectively. Yeah. That's all. Then if you guys got any question now, you guys can sound out, right? Then yeah, I don't want to drag more than 1 p.m. I'm free, but yeah. Any then that will be the end. Yeah.
Any questions, Emma? Any questions?
I think they are good.
If not, then yeah, we can see each other again on Friday, same time. Then but we'll go through the deep learning techniques introduced by Zhiqiang and Prabhu. Yeah. Cool.
Okay, thank
All right.
you.
Thanks. Thank you all. See y'all. Bye.